Hello, everyone, and welcome to the Lifelong Learning and Personalization in Long-Term Human-Robot Interaction workshop, which is as part of the International Conference on Human-Robot Interaction, that is known as HRI. While most of the research in human-robot interaction focuses on short-term interactions, long-term interactions require bolder developments and substantial amount of resources, especially if the robots are deployed in the wild, that is, in the real-world applications. The robots need to continually learn new concepts and abilities in a lifelong fashion to adapt to new situations and personalize their behaviors to users to maintain their interest and engagement over time. This workshop aims to discuss the developments and challenges in these areas and find ways towards making a leap from traditional one-size-fits-all approaches towards the adaptive robots of the future. I am Bahar Irfan. I recently received my PhD at the University of Plymouth and Spaulding Robotics Europe in the Mariet project April. And my research focuses on multimodal personalization in long-term human-robot interaction, which consists of multimodal user recognition and learning and personalizing behaviors to the users in domains such as social assistive robotics and service robotics. Aditi, Ramachandran, my co-organizers, are Aditi Ramachandran, who is a chief robot officer at Robotics, and her research focuses on personalized social robots, robot tutors for children. Sam Spaulding is a PhD student at MIT Media Lab, and his research focuses on personalized cognitive and affective models of users over repeated interactions and across different tasks. Professor Sinan Kalkan is a professor at the Middle East Technical University, and his research focuses on the context modeling and lifelong learning. Next up is Herman Parisi, who is a co-founder of Continual AI and a postdoc at the University of Hamburg, and also working at the MACD Tech Labs, which is a Silicon Valley-based research center established by McDonald's Corporation. His research focuses on human-robot interaction, continual robot learning, and multisensory learning. Finally, Professor Hatice Güneş is a professor at the University of Cambridge, and her research focuses on affective computing and social signal processing, cross-fertilizing research in multimodal interaction, computer vision, machine learning, and social robotics. Part of the organization committee previously organized 2 workshops on lifelong learning and personalization. That is, Sinan, Herman, and Hatice organized the workshop on lifelong learning and long-term robot interaction at Roman, whose website you can see there. And also Aditi, Sam, and I, along with Kengli Koi and Yolanda Leite and Dylan Glass, organized the workshop on personalization in long-term robot interaction at HRI 2019. This workshop combines these topics to find ways that we can further pursue long-term human-robot interaction. We created a great program, and we were first starting out with Oliver Lemon, who's going to talk about conversational leaps in human-robot interaction, a session chaired by Hatice Güneş. Next up, we have full papers session chaired by Sinan Kalkan on topics on personalized social assistive robotics, conversational agents, and adapting language complexity for education, for tutoring. Then we will have another keynote, Zhou, who works at Zhou on cognitive AI assistant and new generation of AI companions, will be sessioned by Aditi Ramachandran. Then we will have another full paper talk. So we had 6 accepted papers at this workshop, chaired by Herman Parisi. And the topics will be on fairness and bias in effective robotics, as well as motion prediction and shared autonomy. We will have finally a panel where with Christian Konati, Yolanda Leite, Gabriel Scanze, Alexander Shruti, and Ogjan Rudovic, who are experts from all of these speakers and invited panelists are experts from industry and academia. It's going to be, the session is going to be chaired by Sam Spaulding, and I'll be the moderator. Then we will have a breakout discussions, engaging discussions in smaller groups on one question: what are the biggest challenges for long-term interactions with robots in the wild? Now, before we start with the first session, I would like to remind you to turn off your video and mute yourselves so that we don't have any distractions with the speakers or the panelists' videos and presentations. And most importantly, enjoy the workshop. And I hope you're going to find new ways and learn and find new ways to further make this leap towards long-term robot interaction. Now I'm leaving the floor to Hatice to start out with our first speaker.
Thank you very much, Bahar. So our first speaker is Professor Oliver Lemon. He's a professor of computer science at Heriot-Watt University in Edinburgh, and he's also the director of the Interaction Lab. This lab focuses on conversational AI, natural language processing, machine learning approaches to spoken and multimodal interaction, and human-robot interaction. He was previously a research fellow at Stanford and Edinburgh universities, and also holds a PhD from University of Edinburgh. Professor Lemon has led several national and international research projects funded by the EPSRC, which is the Engineering and Physical Sciences Research Council of the UK and the European Union. He is an associate editor for ACM Transactions on Interactive Intelligence Systems, and also a faculty advisor of Heriot-Watt's Alexa Prize team, which was apparently finalist in both 2017 and 2018. I'm sure I'm missing some aspects of your CV, Oliver. I try to find as much as possible on the internet, but then I also see you probably will talk about Alana AI yourself without me saying much. But if I forgot anything, you please fill us during your talk as well. And thank you very much for accepting our invitation. And we can start, by you sharing your screen, and then can mute myself.
Okay. Well, thank you very much. I hope you can hear me, first of all.
Yes. Yes.
Great. Okay. Well, thanks very much for the kind invitation and very kind introduction. I will now attempt to share my my screen. I think this will be the right one.
Yes, I can see your screen.
Great. Okay. Great. So thanks again for the introduction, and yeah, it's a pleasure to be able to talk to you today about some of the work we've been doing, which I hope you'll find relevant to your own interests in lifelong learning and personalization and so on. So yeah, I'm director of the Interaction Lab at Heriot-Watt, which is focusing on natural language processing and machine learning, and also a co-founder of a company called Alana AI, which I'll tell you about in a minute. So what I really want to try and focus on in this talk is the types of lifelong learning and personalization we can achieve with conversational feedback, in particular, feedback signals that we get in a dialogue. And I'm going to try to cover very briefly several of the areas that we work in, which I hope you'll find interesting. The first one is going to be about how we learn what to say next in a conversation. So we're fairly well known for work in reinforcement learning on conversational systems, and that's figuring out the decision problem of what to say next. We've also done quite a bit of work on user modeling over time and persistent user modeling, so trying to figure out what interests a particular user has through a conversation system, and that relates to our Alexa Prize system, Alana, which I'll tell you about a bit. We're also working quite a lot on lifelong learning of visual language, so I'll briefly talk about a couple of papers on that topic, and then some work on multimodal deep learning, where we use conversational games to learn latent representations of concepts that combine linguistic and visual information. Okay, but before I get into all of that, just a little bit of kind of background and context about where I'm speaking from, or at least virtually speaking from. So we have a new facility opening in about a year from now called the Roboterium, which is a new building. This is an artist's impression. But what's interesting, I think, is that it's going to have a lot of laboratories for experiments in human-robot interaction. And we're really interested in sort of in the wild, creating realistic environments for humans and robots to interact together. One of those things is we have what we call a living lab, which is a smart home for working on assistive robotics. So there's kind of an advert, which we're hiring for this facility. We're also open for collaboration. And I hope that's one thing that hopefully this talk might spark some ideas for things we could collaborate on. Related to that is you'll hear me talk about Alana. Alana is the system we built, which is our platform for conversational AI research, which we use in both academia and in industry. It was a 2-time finalist of the Alexa Prize, and we then translated that into a spin-out company from the university. Why I hope it's interesting for this audience is that it does a couple of things which are relevant to lifelong learning and personalization. The first thing is that it learns from feedback. So it can learn to do conversational tasks. So the classic thing in conversational AI is you can learn how to, for example, book a flight or find a restaurant or do some kind of goal-based task in a dialogue. You can learn to do those kind of tasks from data, but it can also do open domain social conversation. That was the challenge of the Alexa Prize, was to be able to learn to talk about kind of anything and everything that the user's interested in. So it's also able to do this kind of more social open domain chat as well. It has persistent user models and a long-term memory. So that means if you speak to Alana, say through your phone on Monday, then you speak to it again through a robot next week, it will remember what you were talking about in the previous conversation, what topics you were interested in, and what, in particular, what named entities you were speaking about. So it has some element of personalization in that way. And we use it in a variety of research projects with different partners, including Horizon 2020 projects. It has a ROS interface deployed on lots of different platforms. And I think what's also quite exciting is it has a visual dialogue capability. So if you look in the main or the demo proceedings of HRI, this HRI main conference, you'll find a video of Alana talking about a visual scene and being able to hold a dialogue about a visual scene. So anyway, I hope what you'll hear in this talk will also interest you in potentially trying to use this system in some of your own work. And if that interests you, then please get in touch with me afterwards. Okay, so conversational robots, I don't think I need to labor this point for this audience. We're talking about a whole variety of different kind of embodiments here, ranging from smart speakers to fully sort of embodied robots like Pepper and Ari, to maybe a phone application with a graphical character, or even something like a car, which is a kind of robot that you sit inside, or a smart building. So we've built systems for BMW and also for some large buildings where you're talking, for example, to the whole building through a conversational interface. And all of these things, as far as I'm concerned, are interesting examples of conversational robots for which issues of lifelong learning and real in the wild interaction with real people become very important. And we're interested in conversation because I think conversation is the interface of everyday life, by which I mean, pretty much everybody knows how to have good conversations, and it's a very effective way of doing all sorts of things in real life. So we do tasks, we negotiate with each other, we talk about the visual environment around us, we do social chit chat. We also have lots of forms of kind of personalized entertainment through storytelling and jokes and these kind of things. We do lots of question answering across all sorts of topics and domains. I think another interesting point for this audience is that we very rapidly model our audience and we adapt to the people that we're speaking with. So for example, a young person or a child or an elderly person, you'll rapidly speak differently to that kind of audience. And we do all sorts of teaching and learning in conversation. And what I'm interested in particularly is how we use conversation to teach robots concepts. So conversation is really this, it's the one app to rule them all. It's a one interface that allows you to do all kinds of things. And of course, that's really powerful in the idea of opening up information access to pretty much everybody. So here's an example actually of a system we built a few years ago that shows you how we can use conversation in a very simple way to do a kind of personalization. But I think it's also a fun and interesting example because it shows the problems that come in natural language processing when you're trying to figure out what somebody's preferences and interests really are.
So, Jim, are you more into sci-fi or fantasy?
I prefer sci-fi.
Awesome. Personally, I love Star Wars. But back to you. What is a sci-fi movie that you enjoy?
My favorite sci-fi movie is Blade Runner.
There are two Blade Runner movies, Blade Runner and Blade Runner 2049.
I prefer the original.
Okay, since you like sports, what is a sport that you like to watch?
I prefer football.
Great. Which player do you like?
Any player who plays for my favorite team, which is Leeds United.
Okay, I heard you talk about Leeds United. I think that Leeds United is a 1974 television play shown on October 31st, 1974 on BBC. The film is based on an unofficial strike in Leeds in February 1970. Shall I go on?
Okay, so there you see hopefully an interesting case where it's sort of doing fairly obvious things about asking somebody their preferences and their interests and so on. But then things go a bit off the rails when the wrong referent is picked up for Leeds United. And that shows kind of some of the problems of tracking context in an open domain conversation. It's something we've fixed since then, but I think it's interesting in explaining kind of the challenge of this wide open domain language understanding that you need for user personalization in a sort of open domain conversation. So at this point, I think it's might be nice just to reflect briefly on what's the state of the art in conversational human-robot interaction at the moment. I mean, I think we should be honest. I would characterize it as systems are a bit deaf, a bit stupid, a bit forgetful, a bit rude, and at the same time, they're sort of know-it-all. So when we deploy systems in the wild, we still get quite some important speech recognition errors. But the problems go a bit deeper than that, in that natural language understanding is often still rather shallow, doesn't really understand the full complexity of what people are saying. Lacking access to common sense knowledge, and robots in general are not very aware of their surroundings. There's a lack of real attention to users, in particular the multimodal signals that people are putting out when they're communicating. I mentioned the problem of systems knowing it all. For example, Alana has access to the whole of Wikipedia, so it has a lot of knowledge, but it can bore you by being a know-it-all. Many systems can't really handle more than one person at a time, which makes them not socially intelligent. And there are a lot of systems that aren't really personalized, and in particular, not just in terms of content personalization, but the diverse use of language that happens in real life. the way that different people use words differently is something that we haven't really been able to tackle properly in natural language processing. So all in all, these systems are not really that good at collaborating with humans yet. And why is that? I think one of the main issues really revolves around the notion of context. So context is this word which is used very often. And I think a good way of explaining it is actually a Scottish comedian, Frankie Boyle, recently said that context often means that you really had to be there. And that's really what we're talking about. So let's have a look at this use case for the Spring project, which is a project we're in, which is trying to put a robot into a hospital waiting room. So here a robot will have to really understand that, for example, this is a receptionist, this person is a nurse, these two people are talking to each other maybe, and there's a group of people sitting over here, one of whom may be a patient with their family. So this is a very, very rich, multimodal and social scene, which at the moment we don't have good enough models for. And I think another important aspect is that this context which we have, which would represent this scene, has to be updated rapidly through interaction with people. So these are the kind of models we're lacking right now. And obviously we are very keen to collaborate on building these kind of models. So at this point, some people might be wondering, with natural language processing, about all of the recent news there's been around transformer models like GPT-3. I just want to briefly take a moment just to say that, these kind of models, even though they are very nice and impressive language models, they're not giving us the notion of context that we really need for human-robot interaction and lifelong learning and so on. It's fairly obvious that they're trained on text. They're not multimodal. There are a lot of interesting papers about how unreliable they are, and there are a lot of ethical issues with them as well. But I think from a theoretical point of view, it's important to note that these kind of models are not actually able to deal with things like plans and tasks and goals and social scenes, because they don't really work over abstractions, and they don't do reasoning over the kind of abstractions that we need to handle in human-robot interaction. So what we advocate is using these deep learning models as part of a larger cognitive architecture. So for example, we use deep learning in language understanding and in dialogue management and in language generation, but within individual modules rather than a end-to-end solution. So that gives us a hybrid approach, which is much more controllable, much more inspectable, explainable, and ultimately more trustworthy approach to the natural language processing aspects of a conversational robot. Okay, so this is the kind of standard classic system that we build. We have a speech recognizer, which produces a string of words that's then fed into a language understanding module, and that traditionally produces a meaning representation. The meaning representation is fed into a dialogue management component. This does two very important things. It keeps a model of the context around, and it also decides what to say next in the conversation. Once it's decided what to say next, that dialogue act is also a meaning representation, is sent through a natural language generator and a speech synthesizer back to the user. So all of these components, in particular language understanding and dialogue management, need to be upgraded and updated in order to deal with lifelong learning and personalization. And a really important aspect that I want to draw out in the talk today is how conversational signals that come in through language understanding and dialogue management are actually useful to update a robot's various models that a robot uses. So the conversation can update user models, it can update tasks and plans, and it can even update visual language understanding models. And that's what I really want to try and focus on for the rest of the talk. So it's about allowing language understanding and dialogue management to retrain and update all of these different models that we're using within human-robot interaction. And technically what that comes down to is a couple of things: the ability to process different types of user feedback, in particular repairs. So I'll talk about those in a moment. And then how that interfaces with machine learning methods like one-shot learning and few-shot learning. So conversational signals are really useful. They're a type of feedback that we can use for machine learning, and they can be both explicit and implicit. And the research challenge is to understand these different feedback signals in the context in which they're produced. So let's just look at a few examples here. So for explicit repair, what we have is a combination of some new content and a signal which you can think of either as a reward signal for reinforcement learning or a supervision signal. So some examples of repairs: someone might say, no, I meant 14, not 40. This is nice because it tells you exactly what value needs to be replaced. Or they could say, actually, I'm more interested in Volkswagen vans. Again, you're getting told that there's something wrong with the previous utterance that the system made, and you're getting some more information about the user's interests. But then they can also be very short repair things, just which don't give you that much content, like what? Or no, that's wrong. So then all you really know is that something's going wrong, and you've got to try and figure out what it is. And now that's pretty close to the other type of feedback, which is implicit feedback. And this is something that we really need to work harder on in the field, because we're not very good at all at understanding implicit feedback. So that's things like silences and pauses, gazes, and maybe confused facial expressions, things like that. So if you ask somebody a question and their response is to be silent for a while and then look down at their shoes and look confused, you know that something has probably gone wrong with the question. Maybe it was a bad question or a badly posed question. So this is really interesting because it's continuous online feedback that we're getting to the system, and it's telling us that probably that something is going wrong. Of course, it could be positive feedback as well. You can have smiles and laughter, which mean that your conversation policy is probably quite good at that point. So the question is, how can we use these kinds of signals in learning good models for interaction? So the first thing I'm going to talk about briefly is the idea of dialogue policy learning. The issue is, what should I say next in a conversation? So we did quite a lot of work on this in goal-directed dialogue with Markov decision processes and so on. And more recently, we've worked on this in this open domain social conversation for the Alexa Prize. So the Alana system was trained from user feedback signals. It was trained what to say next in the conversation. And we used a couple of different types of feedback. So as I mentioned before, the sort of explicit positive and negative signals that you can get that tell you whether you're talking about something interesting or whether you said something perhaps stupid in the previous turn. But there's also a signal that we use to do with the length of the conversation. So in this kind of engaging and entertaining dialogue, long conversations are better than short conversations. And we also use this length signal as a training signal. So what we built was a deep learning approach to ranking possible things that the system can say next. And what that's basically doing is looking at these candidate responses. So you may have like 20 different things that you could possibly say next, which come from a variety of different information sources. And you look at the words in the response candidates, also the named entities in the response candidates, and you want to compare them with the previous context. Again, a similar representation of different previous conversational turns. And essentially you want to learn a scoring function on the response candidates that allows you to choose the best response candidate next. So we did that using our system in the Alexa Prize, and we were able to train that system over millions of interactions to actually do a better job, a better and better job at learning what to say next. And the nice thing about this approach is that it can be tuned for other types of conversational domain. So anyway, if you're interested in that work, I just briefly point you to that paper. So that's a type of lifelong learning. It's learning what is a good thing to say next in a conversation, in a particular type of conversation. And I think this kind of method could be extended to several different systems or types of systems. So let's move on briefly, because I think time is short. Yeah, to multimodal systems. So we also want to learn about new words for new objects. And I think an important point for lifelong learning in the wild is that users will have their own personal or idiosyncratic language for talking about objects, and maybe colors and things like that. And we really need to respect the diversity in the population of users and be able to adapt to individuals and how they use language. So we've done a couple of bits of work in this direction as well that I hope is of interest. And in both of these types of work, the key idea is that you get new labels through conversation, or you repair a previous label and then you retrain the model. So it's very simple conceptually that a dialogue manager would be able to tell you, for example, a new label. If the user says, no, that's not a book, it's a laptop, you would get a new label and you would retrain whatever network you're using with that new information. So that's on the machine learning side at a very high level. On the linguistic side, things are pretty tough because you have to build natural language understanding to be able to understand things that humans say. For example, no, the shape is correct, but the color is wrong. So this is quite a complicated thing to understand. So we've built systems that can understand this type of language. And you also have to learn a dialogue policy. So what should the system say next in these type of conversations? So we actually trained a policy that's able to do this kind of thing. The system in this case says, okay, then what's the color? So that was this system. Again, you can find this paper in the proceedings of RoboNLP from a few years back. And it was able to learn colors and shapes through this kind of quite rich dialogue interaction with people. A similar thing we've been working on. So Jose Part is a PhD student of ours at the Robotarium, working on teaching object classes to robots through interaction. And again, obviously the concept is similar. There's a lot of details for which I refer you to the paper, but we can successfully teach robots through dialogue interaction to learn new visual concepts. Another type of work that we're doing in the Robotarium is looking at how we can learn multimodal representations that fuse information from vision and from language. And one way to do that is to play these kind of conversational guessing games. Again, this is a PhD student. He's doing some really good work in this area, getting state-of-the-art results on zero-shot learning for these kind of conversational guessing games, where the point is to try and learn multimodal representations that can be reused for other kinds of tasks. So again, if that's the kind of thing that's of interest to you, then I point you towards this paper. So that was a very brief tour of some of the work that we're doing, which is using different types of conversational interaction to produce signals that allow us to learn better models, for example, of visual language, and to update user models of various types. Okay, and what happens when we try and put this all together? Just wanted to briefly mention the Spring project, which is where we take the Alana system and try and combine it with visual, dialogue, and social scene modeling. So again, you can find this video in the demo proceedings of the HRI conference this year. What we're doing in Spring is we're building a robot that lives in a waiting room of a hospital, and it's able to interact with people to do tasks. So if somebody might say, oh, I'm looking for a place to sit, the robot can look around the room, find some candidate objects, and then through dialogue, explain to the user where they could sit down. And we're working over the next few years on building this out into a multi-person conversational system. And there's still a huge amount of work to be done, but you can see where we've got to so far if you follow this link. Okay, so I think my time is pretty much up. So just to summarize what I wanted to say in this talk, I hope I've got across the idea that lifelong learning and personalization can benefit from conversational interaction. That's probably, hopefully not controversial. Maybe a bit more interesting is the idea that conversational signals can be used to adapt different machine learning models in different ways, but we definitely need richer processing of multimodal signals. We need richer context models, in particular social context models, and we really need to enhance our language understanding and dialogue management components to be able to deal with all of this. So I hope that suggests some next steps for collaboration. So I'd like to work with people on issues such as how we can understand continuous multimodal signals from users to give us some much more interactive continuous feedback for learning. Multi-user human-robot interaction, where we learn social conversations. Part of that is that we don't really have good simulations, at least I don't know of any good simulations of rich social scenes with different users walking around, talking to each other, and so on. Another thing that we'd love to work more on is adapting to individual use of language and the diversity of communication styles and vocabularies that we see in the real world. And I guess all of this comes under the banner of doing real evaluations with real people in the wild. And that's something that we really care about at the Edinburgh Centre for Robotics. And that's why we're building this new building for running such experiments. Okay, so I think that comes to the end of my allotted time, probably gone over time, apologies.
Thank you very much, Oliver. So just sort of thanking you with the clap. I just want to remind everyone, you can post your questions on the chat. We already have a question, so we can start with that. The question is, for the database storing user model and preferences, do you manually build the categories, or do you have a component that abstracts these things automatically?
It's automatically done. We extract, for example, the named entities that somebody's talking about, and then we use an ontology, forgotten the name of it, to figure out what the topic is. So, for example, if I said something like, "Oh, I really love John Travolta," then we would pick up that named entity, extract it, and be able to find that that's an actor. And what film, we use linked entities and linked data. So for example, we'd know that the topic the person is talking about is movies, and we'd also know what movies John Travolta starred in and who directed them. And then we use this linked data to further the conversation. So that's done in an automatic way.
Okay. Another question. These models seem to look at one-way learning. The robot learns from the user, but what will the user learn about the robot in the interaction, and how to account for that?
That's a nice question. Yeah, so what will the user learn about the robot? Well, I think one of the problems we face is that users don't have a very good model of what the robot's capabilities are. So I guess it's the opposite problem, is how to build an interaction that makes it obvious or more easy for humans to understand what the robot can and can't do. So yes, that's an interesting dimension to this whole kind of problem. I think we just need to build robots that are more explicit at explaining their limitations. That's, I guess, what I'd like to say about that.
Okay, then another question. Can you speak to how the dialogue interaction is zero-shot?
The dialogue interaction itself is not zero-shot. So I think the best place to go and look at for work on this would be recent work on transfer learning. So I think in my talk, actually, this paper, if you look for work by Shaliminov et al., you'll be able to see work that he's been doing on, it's not zero-shot learning, it's few-shot learning for dialogue. And the idea is that you take a pre-trained language model like GPT-2 or GPT-3, and then you have a few examples of new dialogues in your domain, and you fine-tune the GPT-2 model to be able to handle these new set of dialogues that you've seen. So there's quite a bit of work. For example, the DSTC-8, the Dialogue System Technology Challenge 8, had a fast adaptation track where quite a few people have worked on this few-shot learning task for a dialogue policy, but it's not zero-shot. No.
Okay, any other questions, please type in. I'll have a final question, and I think we'll probably wrap up the session because I also personally am interested in the implicit and non-verbal aspects. So you did mention about explicit and implicit feedback for repair. I was wondering, in terms of Alana, what sort of implicit feedback does it actually incorporate or is capable of incorporating right now, and how does it do it?
Yeah, so at the moment, the Alana system itself is only working on verbal explicit feedback. And that's why it's something that I really want to collaborate on in the future with people who are doing more, I guess, multimodal signal processing, for example, facial expression recognition and gestures and so on. Because we can see from the data, for example, when people are silent, it's an obvious signal that there's usually a problem. And we know, from human data that facial expressions indicate feedback in conversation. But as far as I'm aware, nobody's really implemented that in a real-time working system. So yeah, that's something that we really want to collaborate on in the future. At the moment, Alana learns only from these explicit signals. Like if somebody says, "Oh, that's great, thank you," that's a positive signal. And if they say, no, that's stupid, that's a negative signal. And I guess the only implicit one is dialogue length. I mean, dialogue length is kind of, it is an implicit signal, but it's actually very useful. It does allow us to train a better policy, but I think we'd be able to do a lot more with immediate continuous feedback from multimodal signals.
Mm-hmm. Well, thank you very much. So for all the Q&A session, the responses, and also for your talk. Okay. So this concludes our session, and I'll now hand over to Sinan to continue with the next session.
Thank you very much.
Thank you, Hatice. Thank you, Olga, for the nice presentation. We will now continue with paper presentations. We have 3 papers in this session. And for each paper, we have 7 minutes for presentation and 3 minutes for questions and answers. Maybe we can start with the first one without any delay. The first paper is titled Increasing Personalization in Long-Term Interactions with a Workplace Companion Robot. The authors are, I hope I'm pronouncing it correctly, Rhian Preston and Naomi, and Rhian is going to present the paper.
Perfect. Got it. Perfect.
Thank
Okay.
you. Can you share your screen?
Yeah, let's. Hopefully this works like I'm tested it to.
Yeah,
Is that
perfect.
perfect?
Yeah,
Okay, good.
yeah, very good.
Wonderful.
Yep, can
So
start.
thank you for that introduction. Hello, I'm Rhian Preston. I'm a PhD student with the Share Lab at Oregon State University, and I'll be talking about the research I've been working on with my advisor, Dr. Naomi Fitter. This work focuses on improving break-taking behaviors through longer-term implementation of an office space companion robot paired with personalization components to improve user adoption. So jumping right into it, we're focusing on social robots in the office workspace. Why? Well, over the last couple decades, there's been a rise in office work and more specifically, computer work. We all spend more time hunched over a keyboard than ever before. So we can see in this lovely image from OSHA Ergonomics. Research within health sciences has shown a wide array of health issues related to sedentary habits, and it has also shown that more consistently frequent breaks can mitigate a lot of these issues. This, of course, has led to a wide array of brand new tools and products marketed at building better routines and habits within the space. Life coaches and other very personalized systems have shown strong results, but are either expensive, unable to scale to the user population, or both. Similarly, phone apps have flourished, offering better schedule keeping at virtually no cost. However, these phone apps have not shown strong lasting results, and instead they kind of fall by the wayside, like most attempts at diets and exercise fads. So if phone apps and humans won't cover all our bases, what's left? Well, I think you know what's left. Robots. Why else are we here? Our lab's past work has shown that on the short term, about 2 days, there's no notable productivity benefits from using a robot over a non-embodied alternative. But the previous version of the system did show that users were happier using the robot than the automated, non-embodied, and non-social system, namely a buzzer system. It also revealed a number of potential system improvements, as well as the need for a longer-term study to determine if, in less technical terms, app fatigue from using all these different scheduling apps carries over to the realm of robots or not. The study at current, we haven't completed it, we haven't carried it out. So this is going to cover more of the system modifications, personalization elements, and then the study design and what we're hoping to see out of the study. So looking at the system design, our actual office space layout, we have a seat sensor on the left, which also includes a control box on the back of the chair. Don't mind how messy that is. That's called lovely research prototypes. And then on the right, we have our actual desk setup. The whole system is run by a standalone mini PC, so we're not interacting with the user's system at all. And it's handling all our logic and recording sensor data. The webcam is not used by any of the logic of the system, but we're using it to record the users during our interactions with the robot for us to examine engagement and interaction after the study is concluded. The button is used as a sort of snooze function, so if the robot interrupts the user while they're in the middle of their work, the user can just tell the robot to be quiet a little longer. And that they're not quite ready. The keystroke sensor that's marked on there is part of our personalization push. So the sensor is just an accelerometer reading keyboard vibrations. So it's to determine if a user is typing on the keyboard or not. And we use that along with the seat sensor to, once a user's been sitting for a certain amount of time, we enter a window where once they drop off on keyboard activity, that's when the robot will try to push in and interject to get them to stand up. And the hope is that this will prevent issues that we saw in the initial study where the system would interrupt the user when they're in the middle of a thought. However, this won't necessarily prevent the robot from interrupting a user, say during a Zoom conference when the user's not typing anything but would really rather not be interrupted. The robot we're using is this adorable tiny Anki Cosmo, which we chose because it's small, but it's fairly robust for a consumer robot, and most importantly, it's clearly very expressive. It's got a bunch of different pre-programmed, pre-made animation groups. And what we've done is we've broken them down into several categories, nominally along negative to positive scale and inactive to active scale. During the study period, Cosmo will perform a random lock of these actions across all the different scales, and we'll use that and how the users respond to them to help determine if the sparse interaction data between those is enough for us to get any possible preferential trends for future personalization. Moving on to the study design, the exploratory studies plan to be a 2-month in-home study for 10 participants total. So 5 of them will use the robot and 5 will use a phone app alternative. The participant pool is small, but for our current scope, an examination of user engagement and robot behaviors, we anticipate that this is going to be a sufficient data amount for us to guide larger study development and further improvements. We'll use a variety of surveys to try and capture participant opinions on robots, as well as their feelings of satisfaction, mood, and productivity throughout the study. The NASA Task Load Index and Self-Assessment Mannequin are both short polls to determine engagement, satisfaction, and mood. But they're really intended for in the moment more than anything else. The Working Alliance Inventory was actually recommended by one of our reviewers, and it fit directly where I was trying to find one more survey to handle a longer term frequency, as well as how well the user feels they're working with the robot. So that'll be supported by some brief daily oral logs that will just help gauge if there's anything unusual going on in the data for the day. So then all of that, okay, what's next? Complete the exploratory study, analyze the results, and then we'll examine what we're seeing in the results from the standpoint of learning preferential behaviors. And on top of that, we're also going to use those results to help further quantify how people are going to emotionally delineate between other people and robots, so we can help look at this from a broader context of how people engage with robots and if they do real bonding in a way that's potentially meaningful or beneficial for building behavioral habits and trends. So finally, thank you to my co-author and advisor, Dr. Fitter, and my lab mates, Brian Zhang and Amir Helmi, for their work on the initial robot design. Excuse me. I could honestly go on for a very long time on this system. So,
I think that's
from spiraling.
That's,
yeah. I'll happy to answer any questions.
Okay, thank you, Rhian, for the presentation. We have a short question in the chat box. Isn't that a vector? I'm not sure what is a vector. Is that a robot?
Oh, yeah. So Vector and Cosmo are pairs. The Vector has a different charger and is slightly different functionality. The
Okay.
Cosmos are either white or that silver gray, and the Vectors have a different charger and are honestly probably nicer, but we've been using the Cosmos, so we've just kind of kept with them.
Okay. How are you planning to use the webcam that you have installed on the monitor?
So the webcam, we're hoping that we can use sparse data and try to do away with the webcam to help with personalization, because the other low-key aspect is we're looking at what we can do for personalized robots that don't require having an upload to the internet or a giant neural network of data or taking gobs upon gobs of user data in order to react or interact. Right now, it doesn't provide any verbal engagement. That is something I want to do in the future. I've been looking at more natural language processing and things to work on that.
Okay. And so one of the, I mean, if the results are promising, one of the issues could be the ease of installation, right? What do you think about that?
So I come historically from a background of actual consumer or larger industrial electronics and robotics. So I'd actually been slowly building setup components to make it as easy to install as possible. So it's plug and play and you just follow some nice one-page instructions. But I'm not that good of an artist. So some of the like nice pamphlets are not as nice and look more like stick figure drawings.
Okay, and maybe we can have the last question from the chat box. Do you want to use Cosmos emotional reactions, and if so, how?
Yes. So a big part of what we're looking at is how people relate or engage emotionally with robots for future work that's spiraling out from this. My interest is a lot more in looking how people empathize and deal with social and emotional interactions with robots. So I want to use Cosmos emotional reactions to see how well, provided I'm understanding your question correctly, I want to see how well those interactions, how people relate to them, and if they relate to them in a way that's meaningful and will help them both maintain their behaviors because of the sort of social contracts you have with another person, as well as then see if those can be used to help people learn or build on their own empathy understanding, as well as then just provide ones that are helpful or pleasant for people, make them feel good.
Yeah, very good, thank you. Thank you. We are looking forward to the results. Thank you for the presentation. Now we can continue with the next one, next paper. The paper is titled Evaluating Conversational Question Generation, CoffeeBot. The authors are, again, I'm sorry if I'm mispronouncing your names, Jelte von Waterschoot, Mariet, Theune, and Jelte will present the paper.
All right. Can you hear me?
Yeah, perfect.
All right. Thanks for the introduction. Yeah, so I'm Jelte Waterschoot, PhD student at the Human Media Interaction Group at the University of Twente. So in the presentation, I will briefly touch a bit on giving the context in the introduction, talk a little bit about personalization, like how it relates to the workshop, the design of a prototype that I made for this personalization, and like some of the pilot results that I had with this social robot. So first off, I'm looking for personalization through casual conversation. So interestingly enough, like casual conversation, often also mentioned like small talk, is a very good way to kind of get to know people, and especially in the long term, having these type of conversations, you can pick up on certain things that people like because they like to talk about their interests. So specifically, I look at long-term conversations involving this type of casual conversation. And then on the aspect of like personalization, how I want to personalize conversation is through asking questions. So one of the things that's found actually in psychology literature is they did a study where they looked at comparing people on, I think it was speed dates, comparing whether you ask lots of questions or not so many questions. And they actually found that indeed, if you ask questions, this is a sign of showing interest, that actually people would prefer to go on a second date. And additionally, and I thought like, oh yeah, this could also be useful for developing like a personal relationship between an agent or a social robot and a person. Additionally, I was also interested in, would this also apply in the long term? Could we have these types of questions, like follow-up questions, with some sort of memory component, such that you can refer back to topics that you talked about or that you know are interesting for the other person to talk about. So one of this work has been done also on building this type of person memory that remembers these kind of casual talk conversations and use that. So for this study, I built like a prototype, which I called the CoffeeBot, which is not a bot for making coffee, but it's located near the coffee machine because it wants to mimic kind of like short conversations you have at the coffee machine, which is like the casual conversation. So I placed this CoffeeBot in the real world at 2 different locations, near a coffee shop and near a coffee machine. The interaction is purely speech-based, so only there's a speaker in there that uses like the microphone and has further speech synthesis. And the idea was to evaluate like questions and how people answer them over time. So the CoffeeBot would have different ways of asking questions. And it's a very system initiative. So the CoffeeBot would like for the participants, they have to scan a card, which could be a student card, and then it starts talking. But the CoffeeBot would ask the questions mostly. And then during next conversations, it will come back to the same topics again of interest. And so in this pilot, we instructed participants to talk at least 3 times over the course of 2 or 3 weeks. At the one location was 2, and the other location 3. But they could do at their own leisure. So whenever they wanted to do this, and the CoffeeBot would have at most like 6-minute conversations. I said min, it should be max. So at most 6-minute conversations. So I wanted to have short interaction, but frequently. But unfortunately, well, there wasn't that many participants because I did this study in the real world during COVID times. So I only had like 7 participants. But anyway, I wanted to briefly touch upon this pilot. So what I did want to have 2 questionnaires, basically one after the first interaction they had and one after the final interaction they had. So after the was complete, and this was about social presence and some others, which we can discuss later. I looked also a bit at the interaction metadata, so how many turns there were, how many interactions, and I wanted to do some post-interview, how people liked it or if they noticed the personalization. But as I said, I didn't get that many participants, only 7, and most of them only had 2 or 3 interactions. So indeed, they said in the interview and from the questionnaire, they liked the experience and the questions were okay, and it was found cute, but what's often with these real world studies, and because there was still the novelty effect because there weren't that many interactions. There were some speech issues as well, in which the robot was quite repetitive, and there was no personalization because there were too few interactions to base this type of remembering and follow-up questions from. So yeah, that was it for me.
Okay, thank you. We have plenty of time. Maybe I can start with some questions that I wrote down while we are waiting for questions from the audience. So how are you planning to continue then? So if you don't have enough participants, will you want to repeat? Or?
Yeah, so one of the things, I mean, waiting until I actually can deploy it in the real world when we get back to normal, because I really would like it to be an entity in a public space. I really like the interaction that people can just walk up to it. So yeah, so that's actually the main thing. Also, some things that I would want to look into is a bit more better turn management, and to give a bit more, even though I said like very explicitly the robot takes the initiative and asks the questions. I mean, you still have users that want to know also more about the robot, for which I had a couple of answers, but it should have a little bit more depth because it might feel too much as an interview for them, like they're being interviewed about all these different topics. And it's like this, not a balance between how much information the user and the robot would self-disclose, for example.
Okay. I mean, currently the robot is not animated, right? So maybe we can try something online in these difficult times.
Yeah, so on another study that we're looking for, and it's with a specific use case for older adults, we wanted to modify like this chatbot to also use speech interaction. And then we want to make a comparison between that. But then these solutions, like having a scalable multimodal application that you can just deploy online is, well, in its infancy, I would say, but we're working on something like that so that at least we can reach a lot of people from home, and we have like this web service running that you can send to everybody, and hopefully we get some more participants in that study.
Yeah, sounds good. I think we can continue with the next one. Thank you for the presentation. That was really nice. And the last paper of our session is titled Adapting Language Complexity for AI-Based Assistance. The authors are Michelle Zhao, Reid Simmons, Henry Admoni, and Michelle is going to present the paper.
Hi, thank you for that introduction. Yeah, I'm Michelle. I'm a PhD student at Carnegie Mellon University. I'm fortunate to be co-advised by Reid Simmons and Henny Admoni. Today, I'm going to be presenting our work on adapting language complexity for AI-based assistance. So machine learning systems are frequently interacting with people. And by doing so, they should learn to leverage information gained from repeated interactions to improve upon the way they interact and communicate with their human partners. Specifically, we're looking at how to design AI systems for personalized coaching. Our overarching goal is to answer the question, how can AI assistants be adapted to the knowledge and cognitive states of humans? So human teachers and coaches must infer and assess their students' limitations and mastery in order to adapt content and teaching style in response. For example, a coach who speaks to a beginner player with incredibly complicated terms may confuse instead of help them. And similarly, a coach who uses far too basic instructions towards an experienced player may frustrate and disengage them. Thus, in order to effectively assist humans, an AI agent should be able to evaluate human behavior and plan actions according to the understanding of its human partners. So in this work, we are using an AI-guided search and rescue task. In general, search and rescue tasks are especially difficult when the rescuers have a limited or obscured field of view and don't know where in the building or environment the victims are. Our search and rescue task is further augmented by victims differing in reward and expiration time, which makes this task even more complicated. And thus, we have an AI that is able to help guide players through this entire task. The two primary tasks in search and rescue are navigation and triage, and our AI coach is going to provide on-screen instructions on how to perform both of these tasks. And we've designed this 2D test bed for our following mechanical Turk study. So when we think about instructions, there are multiple levels of abstraction at which these instructions can be presented. At the highest level, we have room level navigation, then moving down basic navigation tasks, and at the lowest level, motion primitive actions. We provide this grounding example to help understand what we mean by these three levels. So we want the human player to follow the path outlined in red. And at the highest level, we can command them to go to the office. At the second level, we can say something like, proceed to the end of the hallway and turn left. And at the lowest level, we can say, turn right, walk 4 steps forward, turn left, walk 2 steps forward. We can think of abstraction level as complexity, where at the highest level of abstraction, it requires the highest amount of prerequisite knowledge. You need to know where the office is and what is meant by the office in order to be able to understand the level 3 instruction. But at level 1, you only need, well, you don't need any prerequisite knowledge. You can walk 2 steps forward. However, there's a trade-off between abstraction level and length. So the lowest level of abstraction, level 1, requires a significantly longer command, but does not require prerequisite knowledge. And how to adapt to this trade-off brings us to our research question. Does human knowledge affect the level of information abstraction that's suitable for coaching interactions? And can we adapt this to different people? So in this work, we present a closed loop interaction framework that adapts the level of information complexity based on the human partner's observable cognitive understanding. The interaction is comprised of a 2-step process, an evaluate step where the AI infers the intent and understanding of the human, and an adapt step, where the AI adapts the complexity level of instructions presented to the student. So we're going to walk through the first loop of this. In initialization, the AI maintains a control model of the player, which can be multiple parameters, but in our case is a single parameter, which represents the level of abstraction that's suitable. And we generate an instruction at that level, provide it to the player, and observe the player interact with the environment, trying to follow the instructions that we've just given them. Next, in the evaluate step, the instructor's objective is to determine whether or not the human understood the instructions provided. And we do this by assuming compliance of the human. We use goal prediction as a proxy for understanding. The victims are the goals. And assuming the human is following instructions to the best of their ability, the reason they would fail to go to an intended goal or victim is an inability to do so due to lack of knowledge, inability to understand that abstraction level. So using this goal prediction, we can evaluate player understanding and then head back to the adapt step where we modify the level of instruction that has been assigned to them in their control model, which we do currently using a threshold-based level switching mechanism. So taking the posterior probability of the player headed to an intended victim G star, given its trajectory, we can either increment or decrement the parameter assigned for complexity. So currently we are in the process of piloting a study where we're looking at this knowledge abstraction trade-off. We're trying to answer two questions. The first is, how does player knowledge affect, looking at how does player knowledge in terms of preparation, pre-training, and prerequisite knowledge affect the preference and performance of humans when instructed at these different levels. And we are going to be manipulating player knowledge by testing players on memorization of the map and then evaluating their performance. So to conclude, we are looking at machine learning systems that can better leverage insights from repeated interactions. And this is currently a work in progress, and we're hoping for cool results. Are there any questions?
Thank you. Just on time, perfect. While waiting for questions from the audience, maybe I can ask one. So the abstraction levels are discrete, right? Would it be better to make them continuous? And how would you do that if you were to make them continuous?
Mm-hmm. So they're discrete because each of the instruction levels is defined by a corpus of text that we can generate instructions from. It's more difficult to generate these like different instructions if we allow for like a continuous space where the corpus can have, you know, different like weighted combinations of both, of like multiple levels. I think it would make navigation instructions more difficult to generate, but it could allow for more fine-grained, you know, adaptation. So that could be one of our future works.
Okay, sounds good. And how are your experiments are going? At which stage are you now with the study?
Yeah, our study is finalized as far as being able to send the pilot out and get feedback on that. Right now it is 2 rounds. The first is with a static instructor where the levels don't change and participants are randomly assigned to one of the levels. And then in the second round, they'll be assigned to the adaptive coach. And we want to see if there are differences in preference and score that they achieve in these tasks.
Okay. Sounds good. We are looking forward to the results. There's a question in the chat box. How do you maintain an appropriate mapping between abstraction levels? What I mean is, How do you know the lowest level abstraction maps to a mid-level abstraction and then to high-level abstraction? Or are these abstraction levels generated independently from each other?
They are generated independently of each other.
Okay. And why 3 levels? Do you think D3 is going to be sufficient to get some significant results?
Yeah, we believe that 3 is going to be sufficient. I guess when we think about commanding people in terms of like where to go and how to navigate, the first step in this process was sort of just thinking about like how you would instruct someone to go through a building. And the way that you do so kind of maps nicely into these 3 levels. The second level is a bit more encompassing than the first and third, which is, like one kind of issue. However, I guess these 3 levels, if we restrict the second level to a certain corpus, we can maintain that it's approximately the same size as the other 2 levels.
Okay, very good. Sounds exciting. With this, we can conclude this session. Now, I will hand out to Aditi for the next session.
Hey everyone,
Thank
yeah,
you.
I think we're ready to welcome our next speaker. We're lucky enough to have Michelle Zhou. So just a little introduction before we jump in. So Dr. Michelle Zhou is co-founder and CEO of Juji Inc., an AI startup located in Silicon Valley, and it specializes in building state-of-the-art AI technologies and solutions that enable the creation and adoption of responsible and empathetic AI agents. Prior to starting Juji, Michelle led the User Systems and Experience Research Group at IBM Research Almaden, and then the IBM Watson Group. Michelle's expertise is in the interdisciplinary area of intelligent user interaction, including conversational AI systems and personality analytics. She's an inventor of the IBM Watson Personality Insights and has led the development and commercialization of at least a dozen products in her area of expertise. She's also published over 100 peer-reviewed, refereed scientific articles and has 45 patents. And she received a PhD in computer science from Columbia University and is an ACM distinguished scientist. So with that, I'd love to welcome you, Michelle, and we're looking forward to your talk. Excited to have you here.
Thank you, Aditi, for your kind introduction. Can you hear me okay?
Yep, we can hear you
Great.
perfectly well.
Okay.
Yep.
So I'm going to actually share my screen. Okay, yeah,
Perfect.
share my screen. Okay. Can you see my screen right now?
Yes.
Okay, great. So yeah, thank you for actually inviting me. Thanks to all the organizers. And then I just heard actually last talk. It was really interesting. So let me just share my full. Okay, so somehow I got it. Okay, now it's better for me. Everybody can see my slides, right? Aditi, you can see my slides, right?
Yes. Yep, we can see them.
Great. Yeah, so just before I start, a quick intro of my company, a startup called Juji. So Juji is really the AI company located in Silicon Valley, California, in the United States. So Juji specializes in empowering what we call it a cognitive AI assistants. And today, that's what I'm going to talk about. But today's focus is on how such AI assistants can be made into a new generation of AI companions. So this talk I'm going to talk about it is what would be required to do so, and what are potential application areas, and what are the challenges still remaining. 1 second. Okay, so especially for this audience, I'm pretty sure you have seen what's happening in the world given the past just a few years. And this AI assistants literally are everywhere, are ubiquitous. So I just quote one number. 1 out of 4 US adults actually own smart speaker. So like Amazon Alexa and Google Home. And there's 300,000 Facebook chatbots there to engage with customers on the behalf of the different brands. It's because those AI assistants deliver the convenience and novelty, as well as sometimes the social desirability for people who really have a hard time to convey their more sensitive topics or maybe personal topics to a human for being afraid of being judged by the humans. But however, there are huge challenges to actually make today's AI assistants to be a long-term human companions, and even to sustain the long-term human-computer interactions. So for example, most of these AI assistants have a limited intelligence, and we call it normally their interaction with humans are transactional. So like you interact with Amazon Alexa or Google Homes, you will say, okay, turn up the temperature or play a music. Very transactional, very little context. And we call it one-shot interactions. Second part of it is such assistants have a very little soft skills. They may understand what the user is asking in terms of natural language requests. They may even know the goals of the users in terms of, I want to change the temperature, I want to play a music. But they really have little soft skills to understand what is the emotional, maybe a cognitive states, as well as the personality of the users they're interacting with. And the third one is because of a lack of soft skills, they are hardly personal. And another part we also care about very dearly about it is the cost to build and maintain a very intelligent AI assistant. So if it takes a long time and takes a huge amount of financial and human resource to do so, then we would not be able to democratize the use and adoption of the AI assistants. So for the past now almost 5 years now, what Juji has been working on is to create what we call it cognitive AI assistants. And such assistants, we believe, can be made as a new generation of the AI companions that can actually engage users in a long-term relationship. So this basically we wanted to deliver to build this cognitive intelligence, which I will explain what it means. And the second focus for what we are working on is this to support, to enable no coding, rapid setup of such cognitive AI assistants to truly democratize AI, which I also talk about a little bit in this particular talk. So now I'm going to transition to a live demo so you can see what I meant by a cognitive AI assistant. What do we mean by actually democratize the creation and the customization of it? So if you go to gg.ai/login, you can actually try this one, not now, after my talk. So then once you log in, and you will see this just one card because there's no other assistants you have created. So I'm going to create one from scratch. So the context of this one, it is what we call it. I can just select a website deliverable. I want to choose a template. So in this case, it is I want to choose a template in the healthcare, because to demonstrate that kind of a long-term interaction, in particular, I wanted to choose something called a personal wellness assistant. So the idea here it is we want this assistant to engage with the user on a daily basis, to check in on the user. And
Michelle, sorry to interrupt. I don't think we can see what you're doing on your actual.
Oh, really? Okay.
Page. We're just still seeing the slides. Yeah, if you don't mind just switching what you're sharing.
Oh, let me stop sharing and then share again, because somehow, maybe if I share desktop will be, yeah. Can you see my slide? Can you see my screen right now?
Yes, yeah, perfect.
Now you see the demo, right? So I was showing basically not much of a one. Basically, if I abandon this path, I just started. I said that when I started here, and I just have this one card, notice the AI assistants I created before. So I'm going to just start in creating a brand new from scratch. So I select a website deployment. Then I want to find the template. So the template we're talking about it is a healthcare context. I want the personal wellness assistant which can engage with the user on a daily basis and as long as you want. So now I'm going to create such assistant. Yeah, so Aditi, so because you will be my eyes and ears, right? So if you can't see anything, hear anything, just let me know.
Okay, sure.
Yeah. So actually, once you use this template, you already created the AI assistant. So as you will see, this AI assistant can engage with the user already, but it's not customized perhaps to your task or to your context. So I will show you how you customize that. I said, if I say help, I use this one to give you a hint to say this is basically a template, right? Say I'm a demo bot and can answer some general questions. For example, how much do you know about me, right? So now that we started on how are you feeling today? In here it is, they say, I'm feeling great. How are you? So for example, as you can see, without much of a customization, it can actually carries on the conversation already. Great, I'm fine, thank you. What made you feel positive today, right? So the next one I want to say is because I want to customize a little bit. For example, I want to customize this one with assistant to help on women's health, especially, for example, for pregnancy, right? So for women, pregnancy normally is 9 months period, and you want a long-term assistant which can actually care for the women through this period of the time. So then in this case, it is what happened. It is I'm going to QA board. I'm just going to upload one I prepared last night, which have just the multiple questions that you will see. This one, women health CSV, right? I say open. So I say add to it because I want to augment the current demo chatbot's knowledge. Now I augment it because it's a help message. So what happened? You can see here it is. Basically, the CSV file is very simple. You can say question and answer. That's it, right? So now let's go back to the demo one. What I want to show you, it is, for example, if I say, I'll preview again, right? So now this assistant's knowledge is being augmented with the women's health, right? So then if I say help, see? Now I can tell you what's high-risk pregnancy. So now knowledge being augmented. So now, this case, I say I'm okay. I wanted to deploy, for example. So I say generate URL, right? So now basically I deployed. So I deployed one. I want to go to, let's say I wanted to put on a particular, so I want to show you the particular website. So I want to show you how the actually conversation can come, right? Sorry, I don't want this one. So as you can see here, right? So in this case, I would say, so for example, in this case, I want to chat as a Michelle, for example. Today, go ahead. So I want to point out a couple of things. So right now, I'm doing here right now, because in my talk, I will highlight those important attributes a chatbot should have. Also, a cognitive AI assistant really should possess in order to sustain that kind of a long-term relationship building. So as you can see here, it is I'm very cooperative user right now, cooperative user. So I'm actually going along with the flow, right? How are you feeling today? I said it's not so well. Happened today. I said it's just very busy day and too many deadlines. Say, as you can see, and also tries to actually express a certain level of empathy, right? Can do to brighten your day. So in this case, it is, I would say it is, then I would say, what can you do, right? So basically, it's trying to really to follow, it's not just following the flow of the computer, it's also trying to follow the flow of the user. That's how the conversation, how the interaction is supposed to be, even among the between the humans, right? In this case, wanted to hear it? Sure. So basically it tries to cheer me up, right? So attitude isn't bad, it's in beta because it's kind of like a computer scientist geek jokes, right? So I know you're homebound now, we spelled what Joey doing besides this one. So in this case, I might actually interrupt because users are not always very compliant, right? So in this case, I might say, what's high risk pregnancy? Is it what else do you know? So I interrupt. Even I interrupt, but the AI assistant still maintains the context, understands what the one, right? What do you know? Here it's not a completely one. It said is I can tell you what's high risk because they already told me about. So in this case, actually, you can see that AI is not perfect within context. This one because I already said. I already asked about the high risk currency, right? Then I said is help. Let's see if it can give me more information on what it knows, right? Say. Then I will say this one, spare time. And I said is what about you? So I'm going to do what it be context said it because you asked me what do you do in spare time? I said what about you? Which means should understand it is what they're trying to understand, right? So reading people. So they basically like to do, I said, same as you. Again, I want to use the context. That's how actually humans normally interact with each other, right? In this case, I would say, so ask me the one. So I'm going to stop here. Then we can always come back to see more demo. But one of the few, actually I want to say one thing before I go. I said is, how much do you know about me? Remember, I just chatted a little bit, right? So I wanted just to see how much you said is you belong to creators, sensitive, articulate. So basically, but there's only 56 words of me. So if you go back to see the GG Studio, because they go to the dashboard of this one, look at the audience. One person chatted, which is me, Michelle, right? Michelle chatted with one. So I have a personality insights, which to show what Michelle's personality might be based on the current actually chat. This is loading right now, right? So we can come back a little bit to see if it's one coming. Oh, actually it's coming back, right? So take about my big five, and also could be other potentially insights. You can also see it, right? As you can see, this one assistant not only tries to understand the user's natural language text, but it also tries to understand the characteristics of the user and potentially use such information to personalize the engagement in a very deeply manner, right? So then I'm going to go in back to share with you what's behind the scene. So then what I have showing here it is, let me go share with the slide again. So in order to overcome the limitations, what I mentioned earlier, to really allow the AI assistant to engage with users in a long-term relationship, and especially to have the human-like kind of intelligence. So cognitive intelligence refer to having, especially in our context, to actually really power the AI assistants with two sets of the skills, communication skills and soft skills. And in this talk, I'm going to focus on three types of the skills we have been teaching our AI assistants during the past few years. So I will start with the language skills. So actually, this is an article, I'm pretty sure you can find many articles which to show that the language skills, the communication skills, they really help establish connections in a relationship building and maintain relationships, and also actually increase the people's feeling about the relationship satisfaction. So language skills in our context, we identified there are several types of language skills. So one type of it is it needs to be interpreted user input, perform multiple types of tasks. One is open-ended. So for example, if you remember earlier when I showed the demo, I could ask open-ended questions. And in the meantime, the assistant should also maintain its procedural workflow as well. So for example, the workflow I showed you earlier is about the daily check-in routine. It actually asks users, how are you doing today? And what you have done during the day in your spare time. And you can go on with that one, with actually who do you spend time with, what's your blood pressure, and so on and so forth, because I just didn't finish, right? Given a time constraints. So you have to basically satisfy the multiple types. And second part of it is the semantic interpretation. Not only you want to be able to understand the semantics of the one, like all the most of the data-driven models do, but in the meantime, you also want to understand the information in a very fine-grained model. For example, in this case, I gave an example. So if the user asks the assistant to revise their insurance information, to update the insurance information, tell about my insurance new company is Athena and my policy number is this one, the computer and the AI assistant needs to extract this information precisely and incorporate it into the database, right? So basically requires a semantic interpretation as well as the information extraction. To satisfy all those goals, currently we have been using a neuro-symbolic approaches, which means to marry deep learning based approaches with data-driven approach basically, and with a very typical symbolic. So for example, we have a very optimized finite state machines to recognize patterns, to do information extraction, to have to support that kind of precise natural language processing, in this case, information extraction. So we have to actually combine the both. Another way actually, because none of those models will be perfect, right? So you ask other people to develop models. We also could incorporate third-party learning models, third-party natural language generation processing models. For example, we're also considering right now how to incorporate potentially GPT-3 into our model, right? So these are all the things. So if you are working in this particular area, you're interested in testing out your model, and you're most welcome to contact us, because we're open to the third party actually natural language processing and learning models. And now let's go because of time, I'm going to go just really blaze through this one. So the second set of communication skills is very important. It is from a cognitive intelligence point of view, it's called attention and memory skills. So as you can imagine, in a human-to-human conversation, if the users, if the humans who are involved in a conversation do not remember anything, do not keep context, and you can imagine how bad the conversation will go on. So as you can see here, I did show the example very quickly. So what about you? So basically, it's a context sensitive. So I gave you two examples here. What would you like to do in your spare time, which you just saw? But if the context was, what's your favorite movie? If I'm a user, ask the same thing back, then obviously the computer, the AI assistant, they should give different answers. So this means the context, which means the attention has been changed. So the assistant should be automatically detect attention change. But in the meantime, needs to be actually keeping the right memory, right? So this one next example, the right memory. So for example, if I interrupt the computer to say, if you can make an appointment to see a doctor, right? So after this, after helping the person making an appointment for see a doctor, they should go back to the routine and continue today's routine check, right? So if I have a time after this talk, I will continue the demo you just saw, and you will see how this actually works to actually keep the attention, remember, basically help the user to transition from one attention to another smoothly, but it must maintain attention memory to maintain context, right? So this is to ensure task success. For example, if I'm doing routine check, I better, me as assistant, better actually collect the information I want for today's routine, and also ensure users satisfaction in the meantime by actually allow users to shift attention, by remember the users, but by keeping the overall long-term goal of the conversation. So basically help user transition, but in the meantime, keep the long-term memory as well, short-term and long-term memory as well. So right now, actually, in order to support this attention switch and as well as maintain a certain level of a memory, And because it's a challenge, it's virtually unlimited number of tensions, and also a complex context is the user can frequently switch and shift attention. So in order to battle this kind of a problem, it is what we have done is what we call the policy-driven optimization-based approach. So you could actually define a policy. This policy can be based on your long-term tasks, right? So you can actually customize this particular type of policy. So if it's a personal well-being, maybe you want the policy to be relaxed, to let users to express a little bit more. But in a certain type of task, it is, let's say, for example, in the learning tasks, which I actually heard a little bit about last talk, it is, for example, in a coaching session, right? But in that case, because you want to make sure that the users get your coaching instructions, but you might want to make it more rigid to keep the time within check. Because in this case, you want to make sure you deliver the coach instruction within a certain time, allowed minute, and allowed time, versus let the user rambling on, right? So it's basically kind of a user and a topic based. For example, a topic could be coaching about a particular topic, or maybe in the personal wellness about the particular topic, and also could be the goal, right? The overall goal of the conversation, which means you want to potentially to let the users satisfaction more, which is let users the free reign, or versus you want to accomplish the goals of the organizations or the brand, right? So you can actually customize that one. Then we use this methods to automatically manage the context and transition. So which you just saw earlier, I just created it based on template, because underneath the template already have the mechanism to control this also attention shifts and the memory management automatically already. But we will allow the developers to actually specify a different types of a policy to actually change the different optimization goals. You could say optimization criteria, right? You can do that as well. So then I'm going to a last part of it is learning and decision making. So again, many actually articles, many research have found out that social intelligence of a conversational partner and interaction partner really impacts in relationship building and the relationship satisfaction. So which means that if you want your AI to build long-term relationships with the users, and you want to give them this so-called soft skills, also as social emotional intelligence. And how are you going to do that? So right now, we power our cognitive AI assistants with the ability to read between the lines, which I showed in the demo very quickly, basically to analyze on the fly a user's conversational text and infer their personality insights. So then in this case, with the personality insights, will help the conversational AI assistant to personalize the decision making to better help and guide users. So then you might be asking, so what kind of a personality insights I'm talking about? So there are basically three types of the personality insights. One is about people's passions and interests, right? And the second type is about people's skills and talents, which means what people are good at. So certain people are very good at analytic thinking, and some people are very good at actually abstract thinking. So these are different skills, different talents, and different interests. And more, we also try to infer people's styles, if you will, and the way how they handle stresses and challenges, because that's where you can know how to best interact with the person, how to actually establish a kind of relationship. So it's the three broad areas of personality insights. So then how we do that? So basically, and by the way, on the side of this one, I always kind of have a little bit citation of our work, or published work. So then in this case, it's basically our particular approach, current approach, it is big data analytics with a latent trait theory. It's known as item response theory, to use this, what we call evidence-based trait analysis. So you're trying to data mining the evidence, potential evidences in a person's conversational text. Could be a word, could be a word frequency, could be syntactic patterns, could be punctuation marks, Could it be emoticons, right? And it could be the way how they actually answer questions. So you use all this as the evidence to infer what we call the latent trait theta, right? And also to infer the discriminative power of each type of the evidence. So today, because of a time limit, I don't have time to go into the detail, but you're welcome to look up our paper and to see, and what actually is a 2020, I probably want to change this one, to see how the methods work, right? So once you have that insights of the individual users, then you can personalize the conversation and the guidance to the users. This is a way also to exhibit emotional and social intelligence, and also tie back to right now exploring AI. Basically, once you give the advices, give the guidance, the AI assistant should also actually explain why so, right? So for example, I gave 2 examples here. This is in an example of the, for example, coaching users about their interview skills, right? So for example, in terms of the one type of the users might be very assertive and impatient. Another person might be meticulous and indecisive, right? So in this case, it is when they do that, they might want to give different information to those people. They may actually want to give them a quick information versus the comparison of the information, right? So sometimes you want to give a comparison so they can make a quick decision. Another one, you might want to give a summary so actually get them into the information before the next step of the instructions or next step of the guidance. So you can see, once you have that kind of insights and also even explain, right? I basically say, understand you wish to get some quick information. This one says to help you make decisions. So basically to explain why I suggest certain things, why the AI wants to give certain information, certain guidance back, right? So then I'm going to a last part and very quickly because of a time. So as you can see, you saw it already earlier. We really think this is very important, especially for the AI, what I call it equality. So AI, you don't want the AI becomes a luxury items that can be only afforded by certain individuals and certain organizations. So we really want to democratize the AI, especially the creating the powerful cognitive AI assistants with no coding, no engineering effort. So everybody can really create and customize their own. So the one we have figured out, which we call it the formula, which we found has been very, very, very effective. It is you want to be able to create whatever the workflow of your AI assistant. So what I show is that there's a workflow there. And then you can customize the workflow. But in the meantime, you want to also upload. Actually, QA pairs here is a little bit actually a narrow scope. Actually, could be, this one would be user-initiated user initiatives. It could say user initiatives here. You can upload. So which means it is you satisfy both the mixed initiative conversations with your own AI assistance agenda and your users actually agenda. So basically you can have both. Then we can automatically generate an AI assistant with the out-of-the-box cognitive intelligence, which you saw earlier. Right? So this is basically literally 3 steps. And then we want that, because we want this one to enable everybody, especially our organization, to do this one to help their own purpose, right? So now going to last step. Now let's say you have the such of the assistant, as you saw earlier. Then actually the evaluation becomes extremely important, especially if you want such assistant to establish the long-term relationship with users. You want to know how well they have been working on and what are problems they have detected, right? So we want to evaluate this one on the both sides of it, usefulness and usability. So our Tokai article talking about more about the usefulness part of it, right? So it's a goal-oriented performance. For example, task completion rate, engagement duration, and repetition, which means the signal of the failure, potentially the failure. So do you see earlier, I asked the help quite a few times. So this one should be automatically detected to say, hey, why are you ask this one, right? And the operation method and performance, language skills, attention, memory, learning, and this is what I just talked about. But besides the functional evaluation of the AI assistants, we also want to evaluate the user experience and also in turn, and besides direct user experience like such abandon rate, user sentiment, satisfaction rating, also trust-centered ethics. For example, you want to measure the level of empathy, hate speech rate, and user trust rating, because in this case, especially in a long-term relationship building, becomes utterly important. Then how are you going to do that? So our recent work has shown that you can do actually auto-evaluation, which means it is this helps you to debugging the chatbot or debugging your AI assistant, right? So if you're interested in, you can check out our Kai 2021 papers coming out in April, I believe in April or May. And then this is basically automatically analyze all the chat transcripts with your AI assistants, or automatically create what we call the chatbot or AI assistant profile to show you how well your assistant is doing and where you can actually improve it. So actually give you instructions on how you can improve it and give you examples, right? So check that out. And it would be this is the very first step towards this automatically evaluation, because the evaluation becomes a more and more labor intensive and time consuming, and also becomes more and more important, especially in the context of this workshop. If you want to establish long-term relationship, you really want to know how well your AI assistant actually performs. So now I'm coming to my really last few slides. To this community, I wanted to pose an open challenge, because in our work, we have been creating actually this AI interviews, and the longest chat with this AI interview with the job applicant is 3.5 hours. That's our record. And our client has created a cognitive AI assistant doing what we call the digital diary, right? Journal. So her using our platform, her record is 7 days in a row. And every day, this assistant will chat with her clients, her users twice a day, right? 7 days. So I'm going to pose this challenge to the community. Can you create an AI companion or AI assistant exceeding 7 days or exceeding a consecutive, right? And 3.5 hours and a one-time chat. So I'm going to post that open challenge. If you're interested in, you're most welcome to contact me. And I have actually my contact information, just next slide. Now I'm wearing my second hat because I'm currently the editor-in-chief for the ACM Transactions and Interactive Intelligent Systems, which features the human-centered AI research. So if you're interested in a special issue on long-term AI companionship, again, contact me. By the way, I have to say, the special issue from our journal is quite competitive. Right now, we already scheduled, because every year we accept one issue, and now we're also considering this, the issue for 2022, right? So if you're interested in that, you might want to actually ask around and having a team together if you're interested in, and then contact me, and then we can talk more about that. So with this, I'm going to, this is my last slide, and there are still have so many issues we want to address. And also, I want to challenge the community to also jump on these issues as well. One is AI safety, especially with the cognitive assistance, the power of cognitive, as I just showed. They really know about the user, including the user's strengths and weaknesses. But how can you protect the users without harming them? That's one of the AI safety, security one. Second part, AI ethics. So what are the ethical issues may rise, right? So I'm talking about actually both ethic issues, not just the harmful to human, potentially also humans harmful to AI, I'm sure. Is that possible? First one. Second, if the AI grows has its own mind, and would it be that the ethics of the AI got abused? So just thinking about this kind of crazy issues for the longer term research. Another one I was talking about, the companion evaluation. As I said, our current work is really just a very small stepping stone toward a long-term research in this particular area of the evaluation from both the functional and usability point of view, form point of view, right? So I have actually show you some of the recent work, some of recent work about AI safety, AI ethics, and you might be interested in, right? So then I'm going to the last one. It is, even though I'm the person who presenting the work, it's definitely not just my work. It's really the work for a big team. So I have my current colleagues from GG and Huahai, Wenxi and Wei, and also have many collaborators in university as well. So I would want to acknowledge our sponsors, which part of work was really sponsored by AFOSR and also the innovation programs, DoD, and also our investor and Digital X partners on the healthcare initiative. So I'm going to stop here. I think my time is over. I think maybe not off. We started a little bit late too. So
no worries.
Aditi, so
yeah, I think we'll just take a few questions from the audience. I see a couple people have messaged in the chat. So I guess the first question we have is,
okay, I see a chat.
Yeah. Are there common underlying models used across template chatbots?
Yes. Yeah. Great question. So actually, I didn't have a picture showing our architecture. So architecture, it is underlying, we have many, what we call it, hybrid machine learning models, like I showed earlier, right? There is a symbolic AI model, like the fast, optimized finite state machines. And there's a data-driven deep learning models. So that's across the board for all the templates. And not just that, there's a layer on top of the building blocks. So for example, they're about this knowledge, right? So there's a general knowledge of the users. So those knowledge is shared across all the templates. But the domain-specific knowledges are not shared among all the templates. So for example, we have templates for education, templates for healthcare, so that this level of knowledge are not shared across all the templates.
Thank you. And just one more question is, how can you avoid that the chatbot does not become repetitive, saying the same questions and answers over the long term?
Oh, okay, great. Actually, we did have one approach, but today I didn't see this one. As you will see, actually, they will have, this is a very good question. Actually, I have a paper on this one, our article on this one to talking about how do you avoid it, right? So in our case, the simple way is you want to give them alternative expressions. So I don't know if it's still here. If they still doing this one, I will be very disappointed at my chat. Let's see what's going on. So let's say this. Oh, see, this time because it's random, right? So we have some random factor. It is. I can tell you what causes gestational diabetes. Do you remember last time when we say help? We always say this. I will tell you high risk pregnancy. So let's say again. So we have this random factor, but random factor doesn't mean random for a particular person because hey, it's random number. Generally, we have no control, right? So that's why I said it's here is a different one. What's considered healthy pregnancy, for example. So this is different one, right? So this one say help different, it's different type of things. It does say different. So this is one of the simple one. It is you wanted to put in alternative expressions, the simplest one, right? Another one actually. You wanted to potentially to change topic. So as you will see, certain one we have it is, they will say this, can we talk about something else? So you can do switch the topic in the one. Again, as I talked about earlier, depending on the policy, because sometimes you don't want the one, and sometimes your policy might be this, I don't want to even answer. We just say this, oh, can you hold on your question a little bit before we go? That's why the policy you can potentially customize. So basically, we learned from a communication theory, right? You say, so you want alternative, that's one thing. Another one it is you want to just keep it at to control your flow. Another one you can politely just decline, basically to decline their requests. So there's multiple styles and multiple policies you could actually use. And in the meantime, you could also configure our policy to do that as well. Go ahead. Next question.
I think that's it for the moment. I think we have to move on, but thank you so much for your talk and loved the live demo. That was awesome. And yeah.
Okay, great. Yeah, thank you. So I can, I'm not sure if you share the slides somewhere. So I can prepare the slides to be able to share to other folks too, if they want, especially with the references.
Yeah, that would be great. Thank you.
Yeah. Okay, great. Aditi, thank you very much. And then goodbye.
Yeah, thanks again. And I'll turn it over to Herman, who will be chairing the next session of talks.
Okay, great.
Thank you, Aditi. So yeah, we're gonna go directly for the second full paper session. We're gonna be skipping the coffee break, but I hope that many of you are having coffee anyway. So just like the previous session, we're gonna be having 3 papers, 10 minutes each. So hopefully authors just leave some time for questions. So we're gonna go to the first paper called Towards Fair Affective Robotics, Continual Learning for Mitigating Bias in Facial Expression and Action Unit Recognition. That will be presented by Ozgur. Can you, I hope you're there.
Yeah,
can you
I'm
please share your
sharing my
screen? Awesome.
I hope you can hear me very well.
Yeah, great.
Okay.
So stage is yours, and talk to you in 7 or 8 minutes.
Hi everyone, I'm Ozgur and currently studying at Boğaziçi University in Turkey at the Electrical Electronics Department. And today I will be presenting our work. As affective robotics becoming integral in human life and used in applications such as healthcare, education, entertainment, child-robot interactions, these agents must be able to fairly evaluate human affective expressions. However, in particular, facial analysis algorithms are seen to be affected by biases with respect to demographic attributes. The example on the left shows the race bias, where model converts a low-resolution picture of Obama to a white man. In the second example on the right side, 3 different classifiers are evaluated on gender classification ability, and it's shown that darker-skinned females are the most misclassified category. Actually, there have been several methods proposed to solve this problem, such as multitask learning, data augmentation, and adversarial learning strategies. However, there is no study mainly focusing on continual learning as a bias mitigation approach. Continual learning is a concept of learning from sequentially flowing data without impacting and forgetting previously acquired knowledge. In our work, we propose the use of continual learning as an effective strategy to enhance fairness in facial analysis systems for affective robotics due to their ability to balance learning across different domains. We use domain incremental learning settings to train continual learning algorithms for each sensitive attribute. In these settings, model incremental learns to solve the same task, but the input data distribution shifts. As an example of this setting for gender attribute, we are provided with the male and female domains information for each sample, as well as facial expression labels. The task is predicting the correct facial expression for each sample. The data set is split into 2 splits according to the number of domains in gender attribute. In this case, male split and female split. Model first encounters only with the male split, then with the female split, while trying to classify facial expressions in each split with preserving the knowledge from previously learned domain. After training is done, model is evaluated on each split. We conducted experiments using 11 different approaches, including 5 continual learning-based methods. Let's see them. We used several state-of-the-art non-continual learning approaches. Each approach is using the same ResNet-based CNN architecture as a feature extractor, except for the disentangled approach. As our baseline approach, we trained the model under domain incremental learning settings, but without applying any continual learning algorithm. In the offline training case, we used all the data while training the model from scratch. In domain discriminative classifier, an n times m way classifier is utilized, where n is the number of domain and m is the number of classes. In the domain independent classifier case, we are using a multi-head structure in such a way that each head corresponds to 1 domain. In the disentangled approach, the classifier layer consists of separate branches for each domain. However, for the strategic sampling case, it adds a loss weight for each domain inversely proportional to the frequency of that domain. For continual learning approaches, we conducted experiments under domain incremental learning settings, where models learn to solve facial analysis tasks as samples from 1 domain are seen at a time in this training part. We primarily explore regularization-based approaches to make fair comparison with non-continual learning-based methods, as they do not require extra capacity like generative models. Generally, they penalize parameters that are important for previously seen information. We also implement a simple naive rehearsal method that physically stores previous data samples for rehearsal after. To compare the approaches for their fairness on sensitive attributes, we selected the equal opportunity definition as an evaluation metric. Simply, it finds the largest gap among all attributes in terms of scores, the accuracy case, by calculating the ratio of the minimum score to maximum score per attribute. In the example, two methods are evaluated on race splits and the accuracy values are reported. We can simply find the fairness scores by calculating the ratio of the green values over the blue values, identical to minimum over maximum values per method. We conducted two separate experiments comparing the fairness performances of approaches for facial expression recognition and action unit detection tasks with RAFDB and PP4D datasets, respectively. They both provide gender and race information, as well as emotion labels and action units. Each approach is compared in terms of accuracy and fairness measures for both with and without augmentation cases. And for augmentation, images are flipped horizontally in a random manner. All experiments are repeated 3 times, and results are averaged, except for the disentangled approach, because we took the original results from the paper. In the first experiment, we investigate the applicability of continual learning-based methods on learning to correctly categorize 7 emotions, as well as balancing learning with respect to gender and race domains. Results have shown that continual learning approaches outperform other methods on average, with SI performing the best results. Also, even though data augmentation has an overall positive effect on accuracy performances individually, no significant changes observed on fairness scores. In the second experiment, we investigate the performances of models on action unit detection. For the gender splits, the disentangled approach achieves the highest fairness scores. In the case of race splits, naive rehearsal approach, the naive rehearsal approach achieves the highest score owing to the memory-intensive rehearsal mechanism. Even though regularization-based approaches can't be able to perform the best, they still achieve better results than the most non-continual learning-based approaches. Contrarily, more importance is given to fairness for the non-continual learning-based approaches. In this work, we focused on the bias problem in facial tasks and proposed the novel usage of continual learning for developing fair models. We showed that continual learning methods are able to handle the imbalances in data distributions by learning one domain at a time and preserving performance of previously learned domains. Yet, we primarily focused on regularization-based approaches and the naive rehearsal method due to their simplicity for real-world applications. However, it will be interesting to investigate other approaches that are able to better handle long-term adaptations. Also, as a future work, continual learning methods can be used in real-world scenarios with like embedding them onto a humanoid robot and implementing long-term social interactions with underrepresented groups, such as children, ethnic and racial minorities. I'd like to thank my co-authors, Nikhil and Dr. Hatice, for giving me the opportunity to be a part of this research study during my internship. Thank you all for listening.
Awesome. Thanks a lot, Ozgur. So maybe we have time for a short question. And I think in your experiments, you've used a number of regularization methods, and you also have naive rehearsal to have, a fair comparison. Now, the question is, moving forward, like, do you think that maybe more sophisticated mechanisms of like memory replay or, the augmentation of your data through maybe, later representations of the data are a good way to mitigate bias or imbalanced data in large scale data sets? So this is related to your experiments, but also moving forward to a larger scale ones.
Mm-hmm. Yeah, actually, as you said, we can use other continual learning approaches to evaluate the performances of these methods on these data sets. But actually, we used mostly the regularization-based methods because we want to make a fair comparison with the other approaches, because they are not requiring extra capacity and extra parameters like other generative models or other growing other methods that are growing architecturally. So I think.
Awesome. Yeah, thanks. So yeah, in the interest of time, we have to move forward. But if you guys have any questions for Ozgur, just I don't know, you can reach out to him directly in the chat. But yeah, we'll now continue with our next paper, which is improving human motion prediction through continual learning. And that will be presented by Mohammad Samin Yassar. Mohammad, are you there?
Yes. Can you hear me?
Awesome. Yeah.
Cool. Okay. Can you see my screen?
Yep.
Okay. Thank you so much. Hi, everyone. I'm Mohammad Samin Yassar, a PhD student at the University of Virginia. I'm currently working with a collaborative robotics lab under the supervision of Professor Theune. And today I'll be presenting our work on improving human motion prediction through continual learning. So let's start off with the motivation of our work, which is to enable close proximity human robot collaboration. So here we see a scenario where two humans can collaborate and coordinate with reasonable efficiency. And we want to go from here to here, where a robot can also collaborate with humans with similar level of fluidity and fluency. To achieve this, the robot needs to correctly predict human intent as well as human motion, while also having personalized policies for interacting on, as well as predicting human motion. So what are the challenges of human motion prediction and the subsequent personalization? At its very core, human motion is highly stochastic, especially over long term. There are idiosyncrasies in human motion, such as, say, walking style or even gait, that makes each human motion distinct from one another. To tackle this, current state-of-the-art approaches are predominantly data-driven, and they aim to learn a unified representation over training samples, which they hope would generalize over test data. However, generalization comes at the cost of personalization, which is relevant for our domain of close proximity human-robot collaboration. So the question that remains is, how do we leverage large and diverse samples of available data to learn a rich and robust representation, but also allow personalization on a specific human? To address this, in this work, we propose a curriculum learning approach to human motion prediction, where we have two phases. First is we learn an action-agnostic representation from diverse samples of data that can come from any large-scale human-robot interaction or human activity detection dataset. And then we want to fine-tune our model parameters on a new human subject in a potentially new scenario based on that human's data and motion. So let's take a look at our architectures in detail. For the first phase, which is the representation learning phase, we are actually adopting this architecture from our prior work. Here we propose an encoder-decoder framework with discriminators. The input to the encoder is the observed frames that characterizes past motion, and the output is the predicted frames that characterizes future motion. The encoder is tasked to project these observed frames into the latent space, which is then used by the decoder to autoregressively generate future motion. In this work, we aim to capture both continuous and categorical aspects of human motion, and as such, we have a continuous and a categorical latent variable on which we impose specific priors. Say on the continuous variable, we impose a Gaussian prior, and on the categorical variable, we impose a uniform prior. And the overall objective function here is the reconstruction loss as well as the adversarial loss because of the discriminator. So let's take a look at what sort of representation is learned by our framework. So as I mentioned, in this phase, we start off by training on a large and diverse sample of activities that are relevant to human-robot interactions, such as these sort of activities that I'm showing here. The data provided is unlabeled. That is, none of the activity class is known to the framework a priori, and it tries to extract relevant spatiotemporal representation regarding these activities. So here we are actually visualizing our latent space, and what we observe is that not only can it obtain a latent representation that corresponds to these activities, but it also learns to segment the latent space of the activities depending on their semantics. By that, I mean that activities such as walking and jogging, which have similar semantics, have overlapping latent representation. And the same is also observed in other pairs of activities such as bowling and lunging. At the same time, these two pairs are not semantically similar, and as such, they have non-overlapping representation. So this is important because it tells us that we can learn a latent representation even without activity labels. And this sort of latent representation allows us to learn the implicit human intent, which we can use to then focus on the next part of our work, which is where we start to personalize our model parameters on a specific new human. So here we are actually going to use our representation that is learned in the previous phase. And so we are no longer concerned with fine-tuning that. And as such, we do not have any discriminator. And furthermore, we are actually freezing the encoder weights and instead only fine-tuning the decoder. The decoder is fine-tuned here because the decoder is tasked to generate feature frames of human, so in an autoregressive manner. So fine-tuning that would be the most efficient way of using prior knowledge from the first phase and then personalizing on the spatiotemporal nuances of a new human in the second phase. The objective function here is the reconstruction loss. Furthermore, we also train the decoder at a lower learning rate to improve stability of the model. So let's take a look at our experimental setup. We evaluated our experiments on the widely used human activity dataset, GTDM-HAT. For the first phase, which is the representation learning, we trained and validated on 4 subjects. And for the second phase, where we are personalizing on a new subject, we trained on only 1 trial of that subject and evaluated on the held out 3 trials of that subject. And our evaluation metric is the mean squared error. So for our experiments, we trained 2 versions of our model, one with the curriculum learning and one without the curriculum learning approach. And we also compared with the zero velocity baseline. And we evaluated these performance over different temporal horizons to actually see how the model performs over, say, short-term, mid-term, as well as long-term. And what we observed is that the curriculum learning improves the prediction accuracy over all the temporal horizons. And especially the performance gain is significant over the longer term. And this is encouraging because we are using a very small amount of data, but also being able to personalize on a new subject. So in summary, we propose a curriculum learning approach for human motion prediction, where we learn a generalized representation over diverse data samples, and then we fine-tune the decoder parameters on new human subject. Our overall approach learns a rich action-agnostic representation while also performing personalization. Thank you for your attention, and I'll be happy to take any questions.
Great, thanks a lot, Mohammad. So yeah, very interesting work. So maybe a quick question here is, I don't read any questions on the chat right now, but you talked about curriculum learning, right? Mm-hmm. Which for sure, training your system with increasingly sophisticated representations has some benefits. So the question here is in the domain of actions and so on. Do you have any criteria for selecting convenient like actions as you train your system? So what are the criteria for, you know, defining this axis of complexity for actions, which in your case are represented by a 3D skeleton that changes over time?
Yeah. So in terms of actions, we actually decided to go for those sort of activities that are like commonly occurring for any human-robot interaction task, like the ones that we are showing here, and the ones that are available in any large-scale data set. Does that answer your question?
Yeah. Well, we can actually maybe also follow up again for the interest of time. So anyway, thanks a lot. Partially answers. Awesome. Yeah, so now we have our last paper, Situational Confidence Assistance for Lifelong Shared Autonomy, that will be presented by Matthew Sarek. Matthew, are you around?
Hi, yeah.
Awesome.
I'm sharing right now. Can you see my screen?
Yeah, go ahead.
Great. Okay, so yeah, I'll be presenting our joint work titled Situational Confidence Assistance for Lifelong Shared Autonomy. So in our setup, we imagine that a robot arm is deployed in, say, like a home environment to help a human with daily tasks. And so in this video, we can see, so a human was controlling this robot arm to try and move towards this green goal. And then as we noticed by the fact that like the keys isn't increasing after a certain point, so that's indicating that after a certain point, the human was able to stop providing input because the robot was able to realize what they were trying to do and then assist them towards accomplishing it. So the approaches like these are generally successful when the robot arm knows about every possible intent that the human might have, because then accompanied with models for how the human acts under each of these different intents, it's able to look at the human's inputs that it's received so far, and then do inference over the possible intents, form the correct belief, and then assist the human. However, it's a really common case when the human might want to do something which is not already known to the robot. And so in this case, we have a robot arm is being controlled by the human who's trying to take it over to this red bowl over here and pour into it. But as we see, they were unsuccessful, and the same sort of behavior happens. And that is because the same thing happened internally, which is that as the human was trying to move towards this red bowl, the robot had no conception of this red bowl, and it only knew about the green and the purple dots. And although what the human actually did doesn't really make sense from the perspective of either of those intents, it looks relatively more likely for the green one than for the purple. And so when it does intent inference, the same strong belief in the green goal will still result, causing the robot to impede the human in trying to accomplish what they were trying to do. So the key insight of our method is that the robot should measure how confident it is that any of the intents explain the human's input. And then low confidence means that the human should keep control, and then the robot should learn the missing intent. So to describe the method a little more precisely, I'll be writing trajectories as I and intents as theta, and we assume that we have a cost function for each possible intent that the human might have. And so we do intent inference by assuming a Boltzmann user model in which human trajectories, the probability of a human trajectory is, low cost trajectories are exponentially more likely. And then this parameter beta controls sort of the distribution of that. So when this beta parameter is really high, that means that we give really high probability to only very optimal trajectories and very optimal inputs of the human. Whereas when this beta parameter is set to a low value, then it spreads the probability mass equally across both, more equally across high and low optimality trajectories from the human. And so the key to our confidence estimation is actually doing estimation of this parameter beta. And so we derive this formula, which actually has a very intuitive interpretation. So if we imagine that the human's inputs that we've seen so far is this trajectory in blue, and then the optimal continuation of their trajectory is this trajectory in pink, and then the overall optimal trajectory for the entire horizon is this trajectory in red, then what our confidence estimate formula that we derive in our paper says is that it will compare the sum of this blue and this pink to the red. So when these two are very, very close to each other, then we'll estimate a very high confidence, whereas when the user is acting in a way which is not explained by this cost function, then the sum of the blue cost plus the pink cost is going to be much higher than just the cost of the red, and therefore we'll end up estimating a very low beta. And so finally, how that integrates into the assistance of the robot. So we will use assistance methods where we compute an optimal trajectory under the most likely intent, as inferred by the intent inference, and then we will blend that plan, the first step of it, with whatever input we're currently receiving from the human. And so there's a parameter alpha, which we're going to call the control authority, which governs who has control. So alpha 1 means that the human has full control, whereas alpha 0 means that the robot has full control. And so the key to our method to gracefully handling cases when the user is doing something unknown is that it sets the user control inversely proportional to the robot's confidence. And so what this means is, again, going back to those two examples, when the human is acting very close, when the human's inputs are well explained by the cost model that we have, then we will infer a high confidence and then set the alpha to be a low number, meaning that we give control to the robot. And then in the other case, we set alpha to a high number and thus leave control with the human. And then finally, after we've seen a very low, we estimated a low confidence of any of the known intents to be able to explain what the human did, then we use a version of guided cost learning to learn a new intent after collecting some more demonstrations from the human. So to give a quick summary of our method, which we're going to call CASA, the key ideas are that we estimate confidence, and then we use that to set the user's control inversely proportional to that confidence, and then we learn new intents when the confidence is below a certain threshold. So now to go back to this original example, so when we have a known goal, our method performs very similarly to the baseline which I showed you in the first slide, which is that our method is able to estimate a high confidence in the correct goal, meaning that this correct goal does a good job of explaining the human's inputs, and then it's able to give control to the robot and then help assist the user with that goal similar to the baseline. However, in the case with when the human is trying to perform an unknown skill, the difference is that our method performs very low confidence estimates for all the known goals, and therefore it keeps control, user control at 100%, meaning it never takes control away from the human, unlike the baseline. And then finally, after collecting demonstrations, our method is able to then form a high confidence in the new intent that it was able to learn after collecting these demonstrations and learning, and then it's able to transfer control to the robot arm and then assist the user. And so as you can notice, if you look at the top, so both of these trajectories looked quite similar, but actually the one on the right was performed with much less user input because, as you can see, the number of keys is much lower. And so finally, we also did a user study, which I don't think I'll have time to cover in depth, but the main takeaways was that for known tasks, as I sort of demonstrated with these examples, our method generally did as well as the baseline assistance, whereas when there were unknown intents, our method was good as just leaving the user in control and doing no assistance before learning, and then after doing learning, our method was better than full control. And then we also created some subjective metrics, and our participants found that our method after learning was the most understanding, effortless, and useful. Thanks, and yeah, I'll take any questions.
Awesome, great, Matthew. Thanks for presenting your work. So yeah, maybe you have time for one quick question. So for sure, this is really interesting, and the question here is like, how well does this scale up, this approach or a similar one when you have like goals that are, or tasks that are maybe composed of multiple subtasks? So you have shown like how this behaves like with single trajectories, but can you think of extending this to like one task that is comprised of multiple trajectories? And in that case, which additional challenges would you face?
Yeah, that's a really interesting question. I think definitely that would be a very interesting area to extend this work. And I think that the main challenge there is sort of, in terms of the inference of understanding sort of how to break it up. But I think that the same sort of formulas for estimating the confidence would still apply. And I think that, yeah, I think the general framework is sort of very modular in that sense, in that you can sort of substitute different, different user models and different forms of learning the intent. So like most of the derivations and stuff that I showed you in terms of especially estimating confidence only really depends on the user model through just having this cost function. So most methods that are give you some cost function to describe behavior under the different intents, I think would be compatible with this setup.
Great, cool, thanks a lot. I see there's a few additional questions in the chat, so maybe you guys can follow up offline. But for the interest of time now, we have to move on. So thanks to the three authors for presenting their work. And at this point, I'd like to hand it over to Bahar and Sam for the panel session.
All right, thank you everyone. And thanks Herman and to all the speakers from the previous session. We are gonna get started with the panel. So I will just do a quick introduction to our panelists, and I'm flipping through our gallery. It's great to see so many people here, just to make sure we've got them all. But Let's start off with Gabriel Skanse, who's the chief scientist and co-founder at Furhat Robotics. He is also a professor in speech technologies at KTH Royal Institute of Technology. And Gabriel, are you here?
I'm here. Hi.
Yes, great. There you are. Sorry. Ha. Great to have you here.
Thank you.
Next up, we've got Yolanda Leite, who's a associate professor at the KTH, also at the KTH Royal Institute of Technology. And Yolanda?
I'm here.
Is
Hello.
here. Great. Excellent.
Hi, everyone.
We have Alessandra Sciuti, who is a tenure track researcher and principal investigator at Istituto Italiano di Tecnologia.
Correct. Hello.
Alessandra, here, great. Next up, we've got Augie Rudovic, who's a research affiliate at the MIT Media Lab. Augie, great to see you. I see you down there. And could you just unmute yourself and say hi so we know your AV and everything's working?
Hello, hi.
Great. And rounding out the panel, we have Christina Conati, who's a professor at the University of British Columbia.
Hi, everyone. Good morning.
Hi. It's great to have you all here. So I will be monitoring the chat for questions. So we have some, intro questions that we'll field to all the panelists, but participants, please feel free to drop questions in the chat and I'll be monitoring that and we can surface some of those to the panelists. Bahar will be the moderator for the panel. And so I think I will turn it over to her.
Thank you very much, Sam. It's very nice that we have a lot of participation and thank you very much for coming. Gabrielle, Yolanda, Christina, Alessandra, and Augie, thank you very much for being here so that we can discuss ways to make a leap towards long-term robot interaction. And with that, I will actually like to start us off with, could you give a brief introduction about your work, highlighting areas that contribute to the leap towards long-term human-robot interaction? Let's start with Alessandra.
Hi, hello. So what we do with our team is actually investigating the sensory, motor, and cognitive basis of human-human interaction and how we can understand that by using robots, also with the aim of porting on robots some of these human abilities. And connected to the leap, I really think that two keywords I find very useful in my research are the developmental perspective and a social take on cognitive architecture. So from the developmental perspective, what I mean is we can have a look at how children, which are relatively simpler than us, are so good at interacting and learning over time new skills and developing new skills, and use that as an inspiration to try and find out which are the minimal components that we need to have on robots so as to allow them to learn and develop new ones. And the other thing is that for us humans, for human cognition, social stimuli play a special role, have a special importance. And so maybe we have to start thinking of the cognitive architectures that we try to develop, even the basic skills, with a social mindset. So starting to consider social not as an evolution of the ability to interact with the world, but rather as a starting point to let then the system learn to interact with the world.
Thank you very much, Alessandra. That's really interesting with the developmental learning approach. And I think it's really, really relevant for lifelong learning as well, since the robots need to start from scratch and learn as a child as we go. And can I continue with Christina?
Yes. Good morning again. And so I've been doing a lot of work on personalization and AI-driven adaptation in interactive systems in general, not specifically with human-robot interaction, but I still think that a lot of the things that we've been looking at are very relevant for the themes of LEAP and specifically how to enable an interactive agent, and that can be a software agent or for a robotic agent to become aware of the users that they're interacting with, states, needs, anything that is relevant for having an interaction that is more suitable and personalized to the needs of the specific context and users. And most recently, I've become quite interested in also themes of trustworthiness and explainability. So how to enable an intelligent agent to explain its actions to its users, to again create that better, more transparent interaction that can foster trustworthiness and the user being willing to accept what the agent is doing. I think I don't want to go too long because otherwise I go over a minute.
No, thank you very much. It's absolutely great that we can have an expert from HCI, the human-computer interaction perspective, because that actually really translates to robots very easily. It's an embodied version for having interactions with robots. So definitely your opinions are very, very related to this workshop, especially in terms of personalization. Can I continue with Yolanda?
Sure, and just to say very quickly that it's an honor to be after Christina, because she was like one of my PhD. When I did my PhD, I read all her papers, and it's really a huge honor to be now in the panel with you. But so one of the common trends in my research has been robots for real world environments. And of course, that has to deal with the long-term interaction between people and robots, or the more I go into this field, the more I think that maybe we shouldn't call it long-term what we're doing. We're just doing repeated interactions, not really long-term, but maybe that's for another discussion. Also, quite recently, I've been very interested in these aspects of robots learning from non-experts. So if we want to deploy robots into the real world, there's going to be a lot of things that they will not be able to do and that are common sense to us humans, but for robots are really hard. So then how can we leverage these people that are in the environment or maybe not situated in the environment, but can give this common sense knowledge to robots that will be lacking for sure as they are deployed in novel places. So yeah, in 1 minute, I guess that's what I can say.
Thank you very much, Yolanda. That's absolutely, it's a pleasure to have you here as well. Personally, for my PhD, I read a lot of your publications as well as all the others here. So I'm really happy to have you all here in this panel. Thank you. And so can I continue with Gabriel right now?
Yeah, sure. Thank you for inviting me here. So at FERT Robotics and KTH, we are looking at social robots that engage in conversational interaction. And at FERHAT, we have had a lot of collaborations to put FERHAT into real-world scenarios, for example, at train stations and airports, and in doing job interviews. But actually, when I was thinking about it, all of these interaction, I mean, they are not really long-term scenarios, and I think there is a lot of problems that still need to be solved in order to do that, for at least for conversational interaction. It's also not really clear what is possible to build today that actually can sustain for long-term interaction, and part of that has to do with the current techniques for modeling conversational interaction. You can build these chatbots that you can have sort of this small talk with, but small talk is not really engaging in the long run. So current techniques with transformer-based language models like GPT-3 and so on, they are not really built for long term. They are only looking at the current context. So how do you condition it on a more long-term interaction? I think that's a fundamental problem that still needs to be solved.
Absolutely agree. I had the same point of view, basically, that the chatbots, the data-driven architectures are mostly right now, especially for dialogue, are made for short-term interactions and long-term interactions, and that's what we're missing in the machine learning approach that the HCI community or the deep learning community should more address, especially for having robots in the future at our homes. And finally, can I go with Oggy's response on this? Thank you.
Yeah, so thank you for having me here. So my research is mainly about, like everyone's here, personalization, but with a focus on machine learning models and how we personalize those models so that they can be applied to different demographics. And for example, like with individuals with autism, this is something that I've been working on like recently, actually for a few years. How we recognize engagement and affective states, which varies a lot among individuals, typical individuals, let alone individuals on the spectrum. So I've been looking into different ways to personalize various machine learning models so that we can tailor these models to each individual in order to generalize better across the whole population. And there are multiple factors like contextual implications, then single session versus multiple sessions, as well as implications of data privacy, confidentiality, and so on. So these are all different aspects that come into the play when we are building AI systems that are personalized, and I think we should look at all those dimensions when building such a system.
Yeah, the socially assisted robotics is definitely very important for the domain of human-robot interaction, since it's having an impact on the people's life, and it's brilliant work. I actually read that yours as well. As I said, I read all your works, and very great way to combine personalization for engaging children and autism spectrum, children autism spectrum, with the personalization. So my next question is, why should we study long-term interactions? Should be to make robots more engaging, more robust, more accepted, more successful, more data efficient, more practical for future applications, make them more human-like, or any other reasons, please? I will start with Christina.
And let me know if there is too much noise, because there is some trucks going by. So yes, so well, the long-term interaction, I think it's something that it's crucial if we start thinking of these artifacts as becoming part of really, people's everyday lives, right? Where the point is that you're not just having momentous interactions with, in a specific context or situation, but it's something that is really evolving over time, and especially in relation of thinking of these artifacts as becoming some sort of companions that are really part of one's everyday life for the long term. Then this kind of themes are crucial, because it really gets to a point of the agent and the human to kind of evolve together and growing to know each other as the interactions evolve, and as the user themselves evolve and possibly change their states, preferences, and so on and so forth. So I think being able to capture this long-term temporal evolution of the communication is crucial, as it is for human-to-human interaction. So.
Absolutely. That's what we're imitating, actually, with the human-robot interaction, right? The human-to-human interaction most of the time. Gabrielle, can I take your opinion on this one?
Yeah, I mean, first, there are, of course, many applications which do not really require long-term interaction, like robots in public spaces and so on. So I think there is a lot to do there also. But then there are these types of applications, like language learning, for example, is hard to imagine without a long-term interaction, for example. And then I guess there are several reasons, and one is, of course, that it's hard to know whether robots actually do contribute at all over long-term interaction, or whether, especially when you do studies, it's very easy to find people got very excited with a robot the first time, and you might get findings that are not really relevant in the long run. So that, I think, is that's why it's very important to see what happens in the long run.
Especially the novelty effect, exactly. And Yolanda should be perfect person to reply on the novelty effect as well.
I mean, I don't have much to add to what was said. Definitely there's the novelty effect. And I think it's not only the novelty effect, but quite often we run a study, single interaction study, and we claim things that maybe are not true in a month or so, right? Like the effects that the robot had on a particular learning activity or something, will that hold after a week? Or the robot was able to promote inclusion in a group. Do kids still behave like that after 3 months? So of course we should study long-term interaction for the purposes of developing these robots that will make sense into these applications, but also as a more methodological way to sort of like validate our own research, regardless of exactly what is the purpose of the robot, but more to be a bit more systematic in how we validate things in our community. That's what I wanted to say.
You mean the reproducibility? I couldn't say it. Reproducibility?
Yeah, or not even that, right? But like certain things, if you measure just after, like a language learning activity or something, oh, people recall this word, right? But then if they forget in 2 weeks, is that really an effect that we want to say, oh, robots are great at helping this or that? So more about that also, not only reproducibility, but sort of like being a bit more rigorous in, and I'm saying, but I'm guilty. So just saying that as a community, maybe that's another benefit of doing this type of research more often that will come out of, yeah.
Absolutely agree, absolutely agree. And Ogi, can I take your opinion on it?
Yeah, I would like to add to all these great thoughts on the longitudinal importance of the data. It is a very application dependent what we are building. So depending on the application, we would need to define what is the outcome that we want to measure. Do we want to increase the learning abilities of a specific kid? Then we need, that will drive our all design of the models and everything that are to be used to achieve that outcome. And in certain contexts, like in autism, it may be more challenging because there we will need probably much more data to achieve the same outcomes that we would achieve with typical individuals. And as Gabriel also mentioned, if we have public robots, like we don't need to get very emotionally engaged with them or to build some high level of engagement. We just need them to accomplish certain tasks, which are very mechanical. But if you want to perform like a mental health therapy, then we need very much this long-term monitoring and collection of this longitudinal data to achieve to enable long-term outcomes during the intervention.
Definitely agree on the application and domain area. And Alessandra, can I take your opinion on this as well?
I absolutely agree with what has been said before. And I think that this idea that was pointed out about the co-evolution of the two agents is particularly important and can only be analyzed through a long-term interaction. So the fact that, yes, the robot can adapt, but for sure, the user will adapt to the robot. And the interaction itself will evolve over time, as it happens in human-human interaction. And this poses novel and challenging questions. So up to which point a robot should actually adapt? Because it should probably have also its own identity or its own stable model, internal model, that allows also the partner to predict what to expect from that specific robot. And so adaptation has its own risk by themselves, also in terms of trust and how to build it and change it over time. So I think that the long-term interaction is really the way to go if we want to start addressing this kind of questions.
Definitely. And on that challenge point, I would like to ask, what do you think are the biggest challenges for long-term interaction with robots in the wild? And what would be your suggestions towards overcoming those challenges? Alexandra, let's continue with you right now.
I think that one of the biggest challenges is really that of the familiarity. So familiarity is either a nice thing or a terrible thing. So it can be positive as the familiarity that allows us to know the persons we are working with or the agents we are interacting with, so that they are predictable, are trustable, and I can deal with them easily. But on the other hand, it can be boring. So we were discussing about the limits of certain chatbots, and it applies also the limit to some robots' behaviors. If they are too familiar, so if they become stale, they don't change, don't evolve, they stop being attractive. So again, we come back to the lack of novelty effect, the lack of growth. I really believe that balancing this eagerness to change and adapt with stability and identity will be one important challenge to tackle in the future.
Absolutely. To tackle the challenge, we need to have a stable robots, you're saying. That's great. And Ogi, can I take your opinion on this as well?
Yeah, I mean, it would be great to have stable robots, but until we reach that point, we will need to do a lot of modeling and to collect a lot of data about the users. So I think it will be more like, as you mentioned earlier, like an evolving process that we will improve in small steps instead of waiting for an ideal robot to come. But what I find very important is that, at least in the research that I'm doing, I'm trying to also put some limits there. What is the level of, for example, again, I'm going back to that example of engagement. Like, what is the level of engagement that is really needed in a specific interaction? So we don't need always to be able to engage highly or to be able to read human emotions to the like the deepest level. We need just enough to accomplish the task that is given to the robot. And I think that would be very deceiving to, it's also for humans to, if we are building robots that are like a superhumans. So that would be also another thing that brings a lot of ethical and other considerations into the play that we have to be very careful about. So yeah, that's in general how I see those things.
So you're addressing the issue of privacy, I'm assuming.
Privacy is one of perhaps the most important issue at the moment when we talk about personalization, and especially long-term personalization.
And what would be your suggestions towards that?
Suggestions to enable mechanisms that users are completely in charge of their own data, and the caregivers, older people can decide for their kids, parents, what kind of data can be shared for certain studies and so on. But that's the only way to enable a large amount of data that we need to build these technologies. However, we need to give the full right to this data to the users and let them decide what they want to share and how they want to share. But without this data, yeah, we are also constrained in building the better models. So it's a trade-off that needs to be made on both sides. But having that all is designed with good intentions, I believe that is possible.
I want to hop in here because we've got a really good, very relevant question from the chat, which has been going on about should robots in a long-term interaction explicitly be able to be commanded to forget certain things? The role of memory is often included in a lot of long-term or lifelong learning systems, and oftentimes that is about storing data that can be retrieved or replayed or things like that. But forgetting often does not get the same amount of attention. So I think a question for the panel is, what do you think the role of, forgetting? It obviously ties into privacy and the things that you were talking about just now, Ogi, but what do you think about the role of, sort of explicit forgetting in a long-term or lifelong interaction could be?
Can I
just quickly? Oh no, go ahead.
No, okay, go ahead, and I can jump in next.
Just when Sam mentioned this forgetting, it immediately reminded me of catastrophic forgetting in machine learning that we have that happens, especially in these cases when you use this longitudinal data, where we learn one type of behaviors, but then as we are getting more data in the future sessions, then our models keep catastrophically forgetting what we learned before, which is not optimal either. But I think this more relates to the data privacy again. And I think that users should have this right to remove from the robot any kind of information they don't find suitable.
Yolanda, go ahead.
I completely agree about the privacy and that people should know what the robot is storing and all of that. But if we think of like forgetting as a sort of maybe natural way to do it, because that's how humans do, maybe one thing to think about is that not all the things need to be like emulating. So we have mental models of how computers work. We assume that Google will remember things, the Google Assistant, right? Like, why would I think that the robot will forget things when I know that it's a computer that has potentially unlimited storage? So, of course, it might make sense for certain applications. Again, if we are thinking about a pet or some very biologically inspired human, but if we're just thinking of an assistive robot for practical things, then maybe I don't want the robots to forget. In fact, I want the robots to remember what was my appointment 3 years ago or something like that, to retrieve some useful information about that. So it might make sense, but also not all the things need to sort of like mimic human cognition in a way. At least it's my view on it. But also, I mean, and then going back to maybe these technical challenges, we barely manage to make things that work in one single interaction. So in the long term, there's still so many challenges. And one of them is actually, what should we remember, or what should the robot remember? So of course, forgetting is a problem, but that might come some years down the line, I guess, when we actually can store things, not in a very hard code manner, of course, about events and interactions with people and so on.
I completely agree. I mean, this also ties to Ogi's domain-dependent for challenges as well. And Gabrielle, what do you think about this?
Yeah, adding to the, I totally agree about this forgetting that it totally depends on the domain. If it's a social companion, it might make sense. If it's more like a character that you're emulating. Actually, at one point, at Furhat we did a simulated person with Alzheimer, so that people would see what it's like to talk to a person with Alzheimer. So that's definitely an extreme example of that. But when it comes to the technical challenges, I think, again, it depends on the application, but if it's social companions, I mean, apart from knowing how to implement this kind of long-term conversational interaction, it's also a question of what should it be about for a long time, for a longer term. And I don't know if we have enough research even on human-human interaction, what makes a long-term relationship interesting and meaningful, and because that's what we have to emulate then. One of the things that I think is so boring with chatbots is that nothing is at stake. So I can say whatever I want to the chatbot and it will always be nice to me, which is not the case for a human being, and not even a pet. I have to behave towards the pet for the pet to like me. So I think it's the same with a companion, that I would have to sort of do a lot for the companion to actually like me, and then it would be much more engaging to have a relationship with it.
I'm going to tie from the chatbots to Christina. What do you think about it? Since for chatbots, it also applies to robots as well. And what do you would like to see what do you see as the challenges for deploying chatbots or robots in the wild?
So yes, I would like to sort of tie back a little bit into this discussion of forgetting, and that it's really all a matter of applications, right? And again, you have to strike the right balance between having a robot that does that achieves what it's what is required of it. For instance, if we are using it as a simulated agent that can be used to help people practice skills, right? It could even be like a simulated student so that a human can practice becoming a skilled teacher. Students do forget, right? So it's important that in that case, if you want a robot that can be used for practicing teaching skills in a longer term interaction, forgetting could be important, right? On the other hand, as Yolanda was saying, if the application is to have an assistant that really can help me keeping track of all my things, then forgetting shouldn't be in the picture at all. Although it should be in the picture that if I want to remove information that I don't want the robot to have anymore because of privacy, I can do it. But that's different than forgetting, right? It's user's control. But in general, I think another, a big challenge is really this idea of the expectations that are created by the interaction with these agents, right? Because there is this uncanny valley effect that is there, and we don't want to foster in users unrealistic expectations, and how to understand how those expectations might evolve. And that depends very much on different people might have different reactions and different ways to be subject to that uncanny valley effect. So to me, one of the challenges really for chatbot or robot or any other of intelligent interactive agent is really understand how they can be placed in a specific task and context in a way that is good for the users and doesn't generate unwarranted expectations. I think there is research on that, but it's still, there's still a lot of work to do, and it's very challenging how to do it, especially because of the longer term aspects, as Yolanda was mentioning earlier.
And do you think for sustaining long-term human-robot interaction, we need better engineering solutions or a scientific knowledge?
I think it's both engineering solution, scientific solutions, and a lot of also interaction with social sciences, right? Because there is a lot of knowledge that would definitely come even from human to human interaction, psychology. So I think the horizon moving forward, it's really this research should become even more interdisciplinary than it is now. It's one of the, in my view, one of the most important aspects for achieving results that are solid and long-term for scientists and computer scientists and engineers to interact with social scientists, for getting this sort of very broad and comprehensive understanding of all the different aspects that go into this very complex and challenging type of interaction with technology.
Absolutely agree. And from this, I'm going to jump to Gabrielle. As you're also in the industry, I was wondering, how much do you believe the robotics companies or industry has contributed or avoided this area of lifelong learning and personalization? And why do you think that has been the case? What would you like to see the industry to address and to create a leap in this area?
Yeah, I guess that has been a problem for some of these commercial social robots, that they have been placed in the homes of people, where you very quickly sort of get past this novelty effect, and yeah, you experience that it doesn't provide a value in the long run. So that's, I think, a very challenging domain actually to succeed for social robots. I think what we have done is rather to address areas where we don't have these kind of long-term interactions actually. So for example, robots doing job interviews or robots answering questions in public spaces and so on. These are settings where you don't necessarily see this problem that we have. So I think before we actually can address this problem of long-term interaction, I think it will be very hard to place a social robot in the homes of people.
I completely agree. And Alessandra, what would you take on this point?
I would like to connect with what Christina was saying before. and push it even further. I really do believe that this kind of problem cannot be solved if we are not tackling it from a really strongly multidisciplinary point of view. And this entails, of course, psychologists, but I would say also neuroscientists. They can give us very strong understanding of the functioning of at least how we humans do that, but also going beyond this approach, talking with journalists, talking with artists, because they have a different view on what makes a society, talking with anthropologists. So I really believe that the more we aim toward a realistic interaction, like lifelong interaction would require, we really need as much help as we can from different observers of how lifelong learning and interaction unfolds in humans. And this is complex because it's difficult often to establish a positive exchange and productive exchange, but it requires a little effort, but then pays back a lot. So I really believe that this will be a way to go ahead and answering some of our questions. So asking to different fields to work with us.
Definitely. So you're saying artists, so international collaborations, and not just interdisciplinary, but also international collaborations are, of course, necessary in achieving long-term interaction, especially with different cultures and traits. And I would like to actually ask you back to the privacy issue. So what do you think about forgetting? Because you're also working on like the ethical approach for robots.
So are you talking to me, Bahar?
Yes,
sorry.
Yes, I listened to you, sorry.
Okay. No, I really believe that at least for the kind of applications that, okay, of course, it really matters the application, as it was pointed out. And at the moment, I really believe that if we are thinking of a companion robot or a robot that lives and works with us for long periods of time, a sort of autobiographical memory of the robot should be built, which might not mean that it actually forgets things, but rather it provides a story of itself when I'm interacting with it that allows me to grasp at least its understanding of its story and its story with me. What I mean is we often adopt mental models that we adopt for humans to understand these complex autonomous agents. And an all-knowing agent might be difficult to handle for us. So maybe it can be all-knowing on the one hand, but at the same time, it would need to interact with us, helping us to understand its knowledge. In terms of privacy and data, yes, we are working on that because we have realized that we rely on robots differently than we rely on computers. So maybe their interaction itself can push us to be less mindful about, for instance, which data we share with a robot versus a computer. Sometimes even over trusting the robot. We are finding more and more results in this direction nowadays. And so for sure, the entire issue of transparency and of privacy needs to be taken care of, leaving the user or letting the user know exactly and having control on the data shared. On the other hand, a model of forgetting, I think it's really needed if we think of a lifelong interaction with a robot.
Definitely agreeing on all these points. And can I direct it to Yolanda right now, also on the points of what are we missing in the industry, and since you've also been on the industry side and academia side?
I think it's more, we need both for sure. If you look at, for example, the progress in the past couple of years in autonomous vehicles, that was triggered by a combination of good findings on the academic side, but also a lot of investment in industry and all of that, right? So we could expect that for social robots. If that's the case, then we would see like a lot of developments. But then there's also the challenge of think by now we sort of know that all these advances in deep learning, all these GPT-3 that sounds so promising for many like captioning and language applications, do really fail for these sort of like human-robot interaction examples. So in that, we also might need to be thinking of reinventing the wheel in terms of research, or that we might need a few years of research before we actually have sort of like a killer product or a very promising result where then the industry could really like find a perfect use case for. And I guess maybe this pandemic could also be helping in a way many of sort of like situations where humans would be the most common sort of providers of a service, and now it makes more sense to not have humans or something. Maybe some of these situations of the world will also, you know, create good opportunities, but it's very difficult to predict. But I guess a joint effort of everyone will be needed for sure.
Definitely. On the point of humans, we're good at adapting, right? We're good at learning from others. We're good at changing our behaviors and adapting to circumstances. But what about the robots? How should they learn from humans? Should they learn by the humans teaching them, like for instance, through dialogue or demonstration, or the robots automatically, autonomously understand the patterns of their behaviors, humans' behaviors, or how should that be? How should the interaction be through for learning of the robots? So I'll start with Yolanda, since we're just have you here.
I mean, I think as long as they can learn, all of them, all of the above, right? The thing is, ideally, you want to get to a point where, like kids, mostly they learn from example, and they learn by watching others and a little bit by trial and error, but they don't need explicit information or, look, here's a learning session, let me tell you how to do X or Y. But we're super far away from that. So if we can teach robots in other ways, maybe that's also valuable. If you think of like collaborative manufacturing applications and all of that, maybe we can teach people how to teach robots, and then that could also make sense. But that there's so many different ways where we could do it. I don't think there's a perfect way. And again, it depends on the application. It depends on how expert the users that are interacting with the robot, their cognitive abilities and all of that. So I would say all of the possible ones are valid as long as they work.
And what are your take on this for Alessandra? I guess you would suggest a developmental learning approach?
Yes, you got me here. No, but I totally agree with Yolanda. So as far as they learn, whatever is working, it's okay. One thing that I really believe could help is starting to understand that human and robots per se do not share perception. So we often have this assumption that the world in front of us is the same, no, for me and from the cameras of my robot. And so it's enough for me to somehow explain what's there. But it's not true. I mean, our brain is continuously creating a meaning from what we see. I see a movement. I immediately know the goal. I immediately know the feeling, the mood of the person who's moving. I recall my past experience doing the same movement. I live in a sort of socially augmented reality. The robot does not. So I think that the very first step is really acknowledging that and trying to establish a sort of a bridge, a shared perception between the two agents, and then use whatever methods we can to make the robot learn.
Completely agree. And from here, and before we go on to the audience questions, I still have so many questions here. This has been really, really fun and really informative as well. And but I'm going to ask what is the open challenges you think they're important to further lifelong learning and personalization, long-term human interaction? Which ones are the most pressing ones and why? So what are the open challenges? Ogi, let's start with you on this one.
Well, that's a tough one. So there are many open challenges. So everything that we discussed so far is already a challenge for the current robots. But I think on the top challenges side, I think it's mainly data. How we gather and handle the data, and just as an example, if you talk about the data points in human-robot interactions, so it can go into multiple modalities. So what are the modalities that are important? How we collect these modalities? How we address different contexts in which we want these robots to operate? So I think that this is where we are facing a lot of challenges. Having access to this data in a meaningful way that can help us to build better models, but also to deliver technology that will reach some expectations of the users. Because when the users have high expectations, then they easily disengage if the robots are not doing anything close to that. And people who are the end users, in my opinion, they would like to see effects sooner rather than later of these technologies. So I don't think that many of them would actually invest a lot of time in these long-term interactions just for the sake of data collection. So I think this is a big challenge. How we design these interactions so that we can, in a more naturalistic way, collect this data and show to the users that there is a value in what we are doing with this data. I can talk about machine learning challenges for an hour, but I would rather not use very much time.
Yeah, completely. I mean, there are so many challenges, aren't they? But in terms of, I mean, the machine learning is really going fast, but the application on HRI, the robots for using machine learning is actually falling behind. We're still using mostly rule-based methods and not machine learning or data-driven approaches.
I would also make a distinction here, because our community is a little bit has a special flavor compared to the traditional machine learning, because we have also a human component involved here. So we cannot just pipe in ImageNet data set and whatever we get in the output, we tell the kid to do, because that's not, it doesn't satisfy any ethical nor other norms. So we need to be especially careful. So I do like that approach. That we start from simple models and then we go in small steps, because we are affecting human people, and we are not dealing just with counting of the merchandise or whatever.
Definitely agree that we have the human component brings the additional challenge to the systems, the AI systems. And Gabrielle, what's your take on this one?
Now that there are of course many challenges, but you mentioned machine learning here, and of course that's a huge problem for this kind of lifelong learning, because the neural networks are designed to be trained once and for all with huge amounts of data, and then hopefully you have given it all the data it needs. But if you want to add new data points, there is really no good method today for sort of incrementally adding more data and update the model. So I think that's a little bit of a quite a major problem actually. We have one project we are looking at learning new words, for example, or new concepts, or adjusting the vocabulary slightly towards the user. And these things are very hard to do with the current methods. So I think that's a big problem.
I just want to jump in for a second, because Bahar, you said something about the HRI community. It's a little bit behind in terms of using machine learning. There's still a lot of rule-based. And I want to say that using machine learning is one of the challenges, because again, especially the methods that work best today in certain applications, deep learning, the challenge there is really hard to explain what is happening with the model, and therefore to have that level of communication on the robot being able to, I'm not going to say the robot, because we're talking about AI-driven agents, whether they're a robot or virtual. Some of the issues and challenges are very much in common. So as long as you have this AI-driven agent that is doing things for you, right, it's really crucial that at some point you can ask why, right? And the more machine learning driven and the more deep learning based, the more challenging it is to have that kind of communication. There is a lot of, explainability and interpretability of machine learning models is, it's becoming a very, very hot area. There's a lot of work, but still very limited results because we're still at the level of, more like the engineering aspects versus really then evaluating them and seeing how they actually work in the context of interaction with humans. So to me, that of explainability, machine learning definitely, it needs to be a crucial component of any type of lifelong learning. But there is really a shift, even in communities that are using a lot of machine learning, to go back to a mixed approach where there is data-driven, but there is also a knowledge-based component that can make the data-driven part more interpretable, right? So usually I always say, the truth is in the middle. It's not either knowledge-based or data-driven. It has to be in the middle, as it is for humans, right? So to me, explainability is one of the big challenges. There are many, as Augie and others were saying, but if I need to pick one, I definitely, would say explainability and how to bring the success of data-driven approaches in terms of, specific outcomes to also make them more interpretable so that in the end, they really can be part of an interaction that makes humans comfortable and capable of asking for justifications of the AI-driven behaviors.
I cannot agree more. Definitely, it has to be a combination of maybe rule-based, probabilistic methods and data-driven methods to create systems that are both explainable and actually working with humans or long-term interactions. Because as we previously addressed, the machine learning approaches are mostly short-term at this point, at least for dialogue. And Yolanda, what would you think about the challenges?
I don't have much to add other than this sort of like complementing what has been said, right? We use machine learning modules for certain things, right? For the speech recognition part, for understanding where the people are looking at or if they're engaged or not. But then on top of that, we need some sort of like rule-based thing, right? And then if we think about repeated interactions, then authoring all those different like, oh, if this, that, or what should we do becomes a burden. So in addition to all the challenges, there's also just the engineering challenge of building something that works, that is robust enough so that we can deploy it in a real world environment and then collect data and then learn from the people there or all these different things. So in addition to all the challenges, there's also engineering challenges that need to be fixed in order to have some platform that then we could potentially use for greater things.
I always say that actually the HRI is solving one of the most important challenges because each area, the computer vision, the dialogue, they're all very separate and addressing one problem only. And we have the human, we have the interaction, especially for long-term interaction. We need to combine all sorts of information, right? We need to have the recognition, user recognition. We need to personalize the dialogue. We need to learn from the user to adapt our behaviors. There's a nonverbal behavior and so much more, right? And on the nonverbal behavior as well as other challenges, what do you think about it, Sandra?
So I think that this is really a central point. So this entire idea, I don't see it just as a technical or engineering point, but really a philosophical point. So the fact of having a sort of architecture, a cognitive architecture that allows us to make sense, to have a structure for all the different separate modules that do single task, maybe very well, maybe using a single or multiple modalities, maybe using verbal and non-verbal information, something that allows us to make sense of and give sense to the different inputs that arrive at the same time. Because I think that this is the way to move from very specialistic, task-dependent, very good performance that we can observe in certain applications to real generalizability, which is what probably we are lacking a bit at the moment yet in robotics application for HRI. Maybe we have robots that are very good at a certain task in a certain specific applications, but then they cannot generalize as easily as a child would do in doing a different task. I hope that by building a maybe even simple but architecture that can make sense and apply the different processing in different contexts, could really help generalize the abilities of the robot, which I feel is a very, very big challenge for lifelong learning.
So we need to generalizable robots, right? We need generalized systems, not just robots, like Christina saying, systems, both virtual and robots. And Sam, can we have some questions from the audience, please? I know we don't have much time left, but we can have two.
Yeah, I was just gonna hop in to say we only have a few minutes left, and so in the interest of keeping discussion actually rolling into the breakout groups, but we can talk a little bit about Jelte. I want to make sure I'm saying the name right. Jelte had a comment about that connected back to something that Gabriel had said earlier about the lack of stakes in interactions with agents, right? Where it feels like maybe because of lack of technical capabilities, because memory is not so sophisticated, when you interact with the robots or virtual agents over time, it feels like you can say almost anything, right? You can sort of, like there's not as much at stake in your relationship compared to a relationship with, a pet, a real person. So yeah, I think one question I think is, to what extent do you think it would be a good thing for there to be sort of, more substantial, let's say, interpersonal stakes in a long-term human-robot interaction? Is that a future we want to build towards, or is the concept of being able to say, actually erase that, rewind, I have more control in some sense, right? Stakes, this idea that you can't just do whatever you want with this agent, right? The sort of long-term aspect of a relationship. In a sense, that's a giving up of control, right? So yeah, I think maybe Gabriel, since you were the one who brought up that that concept first, do you want to weigh in on that?
No, I totally agree that it's sort of you're giving something away, but you're also perhaps getting something back. Then that you create something that is more engaging also. And you could imagine having a cat that would be happy whatever you did to it. But I think most people find it more rewarding once you get the cat to like you than if you knew that it would do that in any case. And maybe even seeing that it doesn't like others as well as it likes you is even more rewarding. Again, yeah, we are getting into some kind of ethical territory here about robots. Would we like robots that like me more than others, and so on? And that might be more engaging. But yeah, you could. It's also related to this question, of course, of how we behave towards robot, like this example of saying please to Alexa. And of course, you could imagine a system that is even sort of upset if you don't treat it in a nice way. And that in that case, it's not because it's more engaging, perhaps, but because it's sort of teaching me to behave in a proper way. But this could go hand in hand, I guess. So we behave this way towards people, both because it's engaging, but also because it sort of fosters a nice relationship with people. So I think it's something that we will want to model. I don't know if we are there yet, but at some point, I think we want to model that.
And maybe just any more comments on the topic from some of our other panelists before we switch over to the small group breakout sessions, where, of course, we can continue talking about all of these issues. No? Final comments?
Christina, would you like to go ahead?
Well, just going back to this concept of, what's at stake, I can see how in a lot of applications today, there is not much at stake in terms of what you're doing to the robot with what you say or what you, well, mostly what you say, right? But I think there are already applications when there is a lot at stake for humans, right? Because there are applications of these intelligent agents already, for instance, in medicine, where how you decide to act upon the agent suggestions can have a lot of impact on your decisions, right? So there is that aspect to take into account if you're, dealing with a recommender system that helps you to shop online. Well, there is not much at stake. So even for you, right? If you're not understanding the suggestions, if you are accepting wrong suggestions, no big deal. If it's a different type of domain, so we're going back at this domain dependency. What's at stake for the humans involved in the interaction can be very high, even, in applications that are already becoming a reality today. So there is a lot of that needs to go into understanding accountability and, again, transparency and explainability for these artifacts because of the impact on human decision making. And I just want to mention that unfortunately I cannot stay for the breakout section. Sorry.
That's all right. Thank you very much, all of you, for attending. For Christina, Alessandra, Yolanda, Gabrielle, and Ogi, it has been a wonderful panel. We had such great discussions. Hopefully, we'll be able to continue these discussions with the breakout rooms. Hopefully, able to attend. And thanks again for coming to all. And please, for the breakout sessions, turn on your videos and unmute yourself so we can have live discussions and engaging discussions on especially the topic, what are the biggest challenges for long-term interactions and how to make a leap and what are your suggestions on it. Thank you very much. And Sam will now be directing you to your smaller groups. I hope you had nice and engaging discussions in the breakout rooms. Certainly, I learned so many different opinions on different topics people are working on, and throughout this workshop as well, we learned chatbots. We learned about the dialogue, the personalization, the problems in personalization, the challenges, and the solutions to come over to further lifelong learning methods and personalization, long-term interactions from a variety of topics. We had shared autonomy, personalized socially assisted robots, AI-based assistants, as well as small talk robot, and so many more topics. And we learned even more at the panel from our different experts from industry and academia, which was brilliant. I really enjoyed it. I hope you did as well. So if you want to learn more about what has been done in lifelong learning in long-term robot interaction, there is the special issue, the research topic of who's been edited by Hatice, Sinan, German, and Yolanda at the Frontiers in Robotics and AI. And some of the papers will actually receive a notification after the workshop if they will be invited to write their extended versions of this of the accepted papers to there as well as there are other publications there. So please go and check that out. If you're wondering my take on the topic, I actually had very recently a talk at SoftBank Robotics, a heart webinar, where I talked about the challenges and my suggestions based on my PhD for personalization and long-term robot interaction. And you can see it there at the YouTube video linked in there. I know people will also enjoy that one as well. And finally, I would like to thank all my co-organizers, Aditi, Sam, Sinan, Herman, and Hatice, for a brilliant workshop. I personally really enjoyed it. I hope you did as well. And please check out our previous workshops at Roman and HRI, as well as the proceedings of this one, if you would like to learn more about the lifelong learning and personalization. And I hope you continue to work on these topics or make new collaborations for furthering the long-term human-robot interaction and creating the adaptive robots of the future. Thank you very much for all coming here today, and I hope you enjoy the rest of the Human Robot Interaction conference.